Okay, looks like the YouTube is up. Got it all muted. If anybody has YouTube up in the background, make sure you mute it. Otherwise, it'll kind of create this continuous echo, if you will. So. All righty. Good morning, everybody. I know it's a little bit earlier than the official start time, but just trying to bring up all the electronics and make sure all the electronics works. Looks like we got a good number of folks in the attendee list. Thanks, everybody, for your patience. This is what happens when you put a physicist in charge of all the IT. Things don't always go perfectly smoothly. So, but we're slowly getting it figured out. So anyway, welcome. We'll just be sitting here talking informally amongst ourselves for a few minutes. If anybody has any questions in the attendee list, I think if you look down at the bottom of the bezel, there's like a little Q&A tab that'll come up, and you can click that and you can type something in there in terms of questions. There's also a little a chat window, so you can type something into the chat. And we'll be able to see that. We have some folks trying to monitor that. So, but we'll get started here formally here in just a few minutes and let some more people join in. So thanks everybody for joining us. There is a YouTube live stream going on right now. So you can also forward that to folks if some people don't have the ability to use Zoom. So I think the main difference is there will be a 20-second delay from the YouTube broadcast to the Zoom broadcast. So Dylan, I made you co-host for the meeting. So if something comes up, you should have all the functionality that I have. And the same thing is true for you, James. So both you guys are co-hosts. So during the meeting, if you could be monitoring the attendee list, that'd be great.
Thanks, Sonny.
Thanks.
It looks like we got about 27 folks in the attendee list, so some more folks should probably join in the next 5 or 10 minutes. So Pete, what's the weather like over in Luxembourg?
Sunny.
Pete, you're on mute.
Sunny. It's sunny. Sunny. You can probably see in the background of my
I can see
picture.
you, but I can't hear you.
Can you hear me? Can you hear me now?
Yep.
Repeat that again one more time. Sorry, my.
Can you hear me now, Sunny?
I can. Yeah, it was a problem with
You
my.
can see it's also sunny
Okay.
in Luxembourg.
Okay. Yeah, what's so Luxembourg is on Central European?
Central European time, right? So it's
Okay.
about 10 minutes to 3 p.m.
Okay, all right. And then Remo, Italy is also on Central European time, right?
Yeah, 10 to 3 Yeah.
Okay. All right. So
I think this is a good time for us, for sure.
okay. All right. Yeah, I was going to say, Phil and Set kind of got, they drew the short straw with the ridiculous o'clock start time for them over on the Pacific coast. When I was chatting with James and Dylan and we were looking at the different time zones of everybody, trying to get everything aligned just right, we went back and forth, and this just seemed to be the best. So unfortunately, that means Phil and Set get to get up really early, and that means that Duval gets to stay up really late. So
You'll probably see the sunrise coming.
yeah, I definitely could see some stuff coming in the window there. Right. So yeah, I've I remember many a time before working when I was working for NASA, the working with international partners, the Russians liked to meet with us in the afternoon for them, which would mean like a 7 o'clock in the morning start time for us. And then our Japanese counterparts like to meet with us such that it fell at 8 o'clock in the evening our time. So when we had a meeting routinely with the Japanese and the Russians, it made for a very, very long day. You'd have to start the meeting, all the phones would come up and video cons would come up at 7 o'clock in the morning, and then you were working until 10 p.m. at night, meeting with your other counterparts. So when you start to do things globally, it tends to get a little bit challenging, right? So
I think that's probably one problem we will never be able to solve.
right. So Jason, was Gabe going to join us a little later?
I'm not sure. I'll send him a text message and find out.
So Kelvin, how's everything going for you?
Yeah, it's good. Thanks. Raining here in England as usual.
Yeah. I'm really hoping that in the middle of your presentation, your daughters come in and say hello while you're trying to give your charts.
Actually, I booted them out for the day. So
Okay.
my eldest is at school. She'll be home around 3, and then they're disappearing over to the parents-in-laws. So that's great.
Yeah. I think that makes me think of that. There's a video of I think a CNN anchor where he's supporting, and it's in this environment where we're kind of supporting like this, and he's in a room that looks kind of professional, but you see the door open and you see his little daughter walking in, and she's just marching happily into the scene, and they're trying to have a serious conversation on world politics, and so she's just coming to see dad, right? So
yeah,
see mom kind of sneak in and try and grab her and pull her out, but it's like, yeah, we see it. It's hilarious.
Yeah, that happens to me a lot, except the mum doesn't usually stop them. She just lets them come in. And I'm on my own. Yeah. So.
Yeah, both of my kids are just about grown. I've got one that's 19 and one that's 17. So one's at university and the other one is closing in on university. So currently they both are interested in technical fields. So I guess the acorn doesn't fall far from the tree, I suppose. So
Yeah, it's a pretty weird year to start college, right? Or second year, I guess that would be right. Yeah.
You're right. Absolutely. It has been very bizarre for kids, both in high school and at university, right? At Texas, we have kind of a mixed bag of how they're doing it, right? So they're just trying to make do, I guess. And it's hard to think, it's difficult for students to get the same type of interaction when they're doing things remotely versus being in a room with an instructor where they can talk or interact and so forth. So it's definitely been a little awkward and challenging, right? You know, ideally this could have been an in-person meeting. That was the hope and expectation, but we just simply do the best we can and try and make forward progress, right? So good morning, Joe. How you doing? Joey Lob from Texas A&M.
Howdy.
Hey there. How you doing? Good morning.
How are you?
Oh, not too bad. Not too bad. We're just gonna we'll get started formally here in just a minute or two. We're just kind of chatting amongst ourselves, sipping on some coffee, and we'll get started here formally in just a second.
Excellent.
Sonny, just a question from one of the attendees. Is the video of the presentations available to view on demand afterwards?
So yes, my hope and expectation is that I don't do something to screw it up, and we can actually port over everything to our YouTube channel. So the intention is for the YouTube broadcast now, once it gets completed, I'll go in and probably try and annotate it to break it up by talk, and then it'll be available on our YouTube website so folks can take a look at it later, right? So that's certainly the hope and expectation, but there could be a problem with the organic interface here that causes a problem. So, but hopefully I'll get it right.
And just a note to the attendees, if you can put your questions in the Q&A part at the bottom of your Zoom screen, as opposed to in the chat. Thanks very much.
Thanks, Dylan. Appreciate it. Well, let's go ahead and just get started. It's 7:58. We have a kickoff time of 8 o'clock. So we'll just go ahead and get a couple minute jump start here. First off, everybody, thank you guys for joining me here this morning. I know for some of you guys, this is very, very early. So Phil and Set, thank you for joining us very early. And for some of you guys, it's just the middle of the day. And for Yuval, who's going to be staying with us until midnight tonight, we thank him for his time. Currently he's teaching right now. As soon as he gets done with his class, he'll be joining us for the midday session. So thank you all of the performers for joining us, and thank you for pulling together some presentations to talk to us about. I'm excited to hear all the different things that you guys have to tell us today. I'm hoping for a good, productive discussion. So it'll be neat to share some of these forward-leaning ideas that we have with one another, right? Collaboration is always much more effective, right, than just somebody working by themselves. So as we get together and exchange ideas and talk about things, I think it just inspires each other on different things that maybe we had not thought of. So it's pretty neat that we can do that. Now, as I was just saying a few minutes ago, we certainly hoped that we could have done this as a in-person meeting, but I guess since we all think about things that are on the frontiers of engineering and physics, we're no strangers to adversity. So sometimes when you're faced with a problem that you just can't get around, you find some way to try and make forward progress. And so this virtual meeting is a way for us to do that. And I think although it's not as good as doing things in person, it's certainly effective. So thank you guys for working with me to get all the technology zeros and ones taken care of and making sure everything works. I think this broadcast we're doing today will benefit from all the stuff we did trying to get ready for this. So let me, I'll pull up some charts here to get things started. Bear with me while I try and make sure I share the right screen. All righty. Can everybody see that?
Yes.
Okay. All right. So unfortunately, the screen that I'm presenting on is over here. I may flip back and forth. So I'm going to try and make sure I have good Zoom protocol and look at the camera. So, but if you see me doing that, that's why I have that. I have a screen over to my left here. So anyway, so again, welcome to the inaugural kickoff meeting of LSI's Interstellar Initiative grants. We have, I think, a lot of neat things to talk about today. This is just a quick snapshot of the schedule. This should also be in the meeting notice that I sent out. You should have all this information in a little table that's been embedded, but we'll just talk about it really quick. See if I move my, can you see my mouse here when I do that? Okay. All right. So we've got for the day, we have in effect 2 sessions. We have an early morning session of 4 20-minute talks, and followed by a little 30-minute Q&A session. And then after that, we have 5 talks after a short break in the midday session. And I guess morning and midday is relative, but this is for Houston time. We have 5 talks midday, followed by another Q&A. So a lot of interesting things to talk about. These will be 20-minute talks. During the Q&A session, I would request that when we get questions, let's keep the questions focused on the technical materials, make sure they're respectful, and try and keep them relevant to the previous session that the period is associated with. So the early morning Q&A will make the questions pertinent to the 4 previous talks. And then in the afternoon, midday afternoon session, keep the Q&A relevant to the 5 preceding talks. And that'd be great. And then, as Dylan said, for you folks in the attendee list, there is at the bottom of your Zoom window, there's a little button that you can click that allows you to type in questions, and then it'll allow Dylan and James to kind of make sure we catch those and do the best we can to try and answer those. So that's a way to do that. There is a chat window. I know there's also a chat window on YouTube. I don't know how effective we'll be at trying to monitor both of those. We'll do the best we can, and just bear with us. This is kind of a first for us. So hopefully we can at least get most of the functionality and try and interact with you guys as much as we can. So. All right, so before we get into the presentations, I just wanted to spend a few moments to talk to you guys about Limitless Space Institute. What is Limitless Space Institute? What makes us tick? So let me just kind of jump in and go through some of these slides here. So Limitless Space Institute, our vision, right? We hope and aspire to advance human exploration beyond our solar system, and that is a very challenging vision, to be sure. And I think that certainly helps maybe put in context why we have such an interest in power and propulsion the way that we do. In terms of our mission, we hope to achieve this vision by inspiring and educating the next generation to travel beyond our solar system and to support the research and development of the enabling technologies that supports that type of an objective. Integrity, courage, and imagination, these are all very important to us. It certainly takes a lot of imagination to try and think about what's beyond what we know and what we understand. And it's difficult sometimes because we're out in the unknown, and there's no textbook, if you will, to help figure out some of the things that we're trying to figure out. Our pinnacle objective, our big, hairy, audacious goal, I call it a North Star, if you will, is to ideally enable interstellar travel by the turn of the century. So very noble objective. It kind of calibrates everything that we think about and that we do. Certainly something that's worth pursuing. So now when you talk about human exploration of the outer solar system and on to the stars, the distances that we think about are just so different from most of the things that we are confronted with when we talk about human space exploration today, right? We're in low Earth orbit, and we're talking about going back to the moon, and occasionally we talk about Mars. And so the distances associated with just those types of destinations are very different from when you talk about the outer solar system, right? When you get what I call past the frost line in the solar system, that's like the asteroid belt, if you will. If you want to go out to the gas giants and deep into the outer solar system, these distances are just mind-boggling compared to some of the stuff we typically think about when we look at human exploration. And so that means in order for us to move humans around the solar system in time frames that are compatible with us, right? The amount of energy we have to put into a spacecraft and take out of a spacecraft to get it going from Earth to any destination is absolutely mind-boggling. Much, much higher than anything we've been confronted with in the past, right? Getting to getting to low Earth orbit, the delta V is in the 9 km/s range, right? And that's very challenging when we look at how we try and accomplish that with chemical propulsion. You have staged rockets, a lot of high energy density as we try and climb out of the gravitational well. But when you talk about sending a human being to Jupiter or Saturn, the distances are so big that the delta V, in order to do that in a year, if you will, to leave Earth and get there in a year, you're almost an order of magnitude higher, just talking about the first edges of the outer solar system, let alone if you wanted to do something much further out. So all that to say, the physics of that challenge is monumental. And so we need to have significant improvements in the power and propulsion systems that we try and bring to bear to solve that problem, right? A mission planner will go through and try and get together some technology to accomplish a mission objective. And when you throw delta V's that are, instead of 9 km/s, what if it were 50 km/s or 100 km/s? Those are, vastly larger delta V's. You need propulsion systems that have high specific impulse, or at a minimum, are very, very fuel efficient. And as is often the case with some of the things that we would bring to bear, you need to have some type of persistent power source to couple to the propulsion system. So all that to say, I guess the coffee cup expression is we need to establish the ability to go incredibly fast. Now, if we try and codify the technology trade space in as simple a way as we can, this infographic is kind of meant to give you a window of insight of how Limitless Space Institute kind of looks at the technology options that we might use for having human exploration in the outer solar system and beyond. Now, let me make sure I highlight that. I said human space exploration, and so the power propulsion concepts tend to be very centric to these large mass systems. I'll talk about sails in just a second, but going from left to right here, we have 3 swim lanes, and they kind of span the waterfront of physics and engineering, going from known physics, known engineering, to unknown physics and unknown engineering. And in the leftmost swim lane, right, we have fission. And so this is just nuclear reactions, nuclear reactors, if you will, fissioning uranium or whatever appropriate fuel you've got. And if you look at my little cartoon here, there's a little red glowy bit. That's a technical term. A little red glowy bit that's kind of representative of some kind of a nuclear reactor that's providing power, and it routes power to some electric thrusters that take that power and accelerate propellant to very high speed. So it's very high specific impulse, very fuel efficient. And so this allows you to be able to put in a lot of delta V into a spacecraft. And so this is based on known physics and known engineering. We have nuclear reactors, and we've actually flown a very, very small nuclear reactor in space, SNAP-10A. But when we talk about human space exploration, the power levels that are going to be necessary for supporting human space exploration, even when you're talking about Mars and just starting to get into the frost line of the solar system, you're talking megawatts of power levels. And so, the nuclear electric propulsion has been studied a lot in the literature. And so in terms of an anticipated power range, something along the lines of 2 to 50 megawatts. And to calibrate that, a locomotive, when you're sitting in traffic at a railroad crossing and a locomotive goes by, your average locomotive is about 2 megawatts. So to kind of put a megawatt or 2 megawatts in context, that's a locomotive's worth of power, if you will. And so nuclear electric propulsion would enable human exploration in the outer solar system. It would enable what we call interstellar precursors. There's a 1,000 AU there. That means astronomical unit. So an astronomical unit is the distance from the Earth to the sun. And so some of the first interstellar precursors that were talked about, I think a JPL study, 1,000 AU looked at putting some kind of a probe at 1,000 astronomical units. I think Voyager 1 is just past 140 astronomical units today, and it's taken it several decades to get there. So that really, I think, starts to put things in context. But moving from the left swim lane to the next one, actually, before you let me jump back, there's a footnote there. I've got NTP, SEP, and BEP. Some alternatives to nuclear electric propulsion is nuclear thermal propulsion. That's where you use a nuclear reactor to directly put heat into a propellant. So that's an additional fission-based propulsion system. Solar electric propulsion is where you might use solar panels. The only downside is the intensity of sunlight gets less as you get further out from the solar system, so that it has limited functionality. And then beamed energy propulsion is another way where you keep the power source at home and you beam power to a spacecraft that would have some tailored collectors that would collect that energy and then feed it to some electric propulsion systems. So now moving to the middle swim lane there, we've got fusion. That's where we would replace the nuclear reactor with some kind of a fusion process, where we would have a reactor of higher power jumping up into an appreciable fraction of a gigawatt. So 50 to 500 megawatts, maybe even more, a lot of locomotives. One additional permutation on that would be, instead of having the fusion reactor providing power to some thrusters, another iteration would be to simply have the fusion reactor to directly accelerate the propellant. So the actual burning process of burning the plasma, burning the fuel in the reactor, the reactants could be expelled out of the fusion process. And so that could be a direct fusion type of approach. We'll actually talk about some of those today. Now, this is known physics, but it's a little bit more challenging in the engineering field. I wouldn't say unknown engineering. I think we've made a lot of good progress in the last 70 years of plasma physics development. Fusion is certainly a very useful power propulsion tool. It can enable fast human exploration of the outer solar system. And it actually would enable interstellar that could occur in an appreciable fraction of a century, many decades, if you will. So very, very high interest to Limitless Space Institute. Then you get into breakthrough. If I, to visualize physics today as a Venn diagram, you'd have two circles side by side. One would say general relativity in it, that kind of governs what goes on in the macroscopic world. And then the other one would say quantum mechanics, and that's what governs what goes on in the microscopic world. And really, they don't overlap, right? And so that tells us that there's maybe a more generalized understanding from the Venn diagram perspective of nature. And if we can develop an understanding of what that might be, that might give us some different ways to come up with approaches that would allow us to do something in a power and propulsion type domain that might make this challenging task a little less challenging, right? Think about quantum mechanics gave us the ability to connect with iPhones, and general relativity gave us the ability so that we had GPS and we don't get lost when we're trying to make it to our favorite restaurant. So in the process of working on the frontiers of physics, maybe we can come up with something that might make the idea of a space drive possible, or a wormhole, or a space warp, and perhaps that might enable some type of faster interstellar type of transit times. Now, on the very bottom there, you see the word sails. While Limitless Space Institute is very, very interested in human exploration, the solar sails do address the ability to go incredibly fast, and they directly trace to interstellar missions, and so that is definitely of interest to Limitless Space Institute. I kind of liken this to when your kiddo goes to college. They oftentimes will pick a major, but they also pick a minor because they're very interested in that as well. And so maybe this is your kiddo picks engineering for their major, and they pick mathematics for the minor, or the other way around. So that's kind of the way we look at things. Now, I know there's probably 2 or 3 different things that other people would say, well, what about this or what about that? We're just trying to keep it simple and help you understand how LSI looks at it. This is just a snapshot of some of the programs that we have. A lot of research and development focus from Limitless Space Institute. In terms of internal research and development, we have a lab called EagleWorks. Currently, we're doing some work for DARPA. We'll talk a few more minutes on that in just a second. And then, of course, we we want to directly fund external research and development, and we're doing that through the Interstellar Initiative grants. And that's the purpose of today's meeting. You can kind of see some of the grants that we picked for funding as part of our inaugural round. University partnerships, we do want to collaborate with the universities and try and find different topics of mutual interest that we can kind of lean in together and do some work that traces towards our pinnacle objective of enabling human exploration of the outer solar system and onto the stars. So right now we're in the process of working with Texas A&M's Nuclear Engineering Department. We want to focus on trying to do some development work on a 1 to 10 megawatt electric nuclear reactor. Student programs, we intend to host interns, graduate students, postdocs here at Limitless Space Institute. At some point, we do want to develop some course materials in the form of maybe some week-long or 2-week-long courses during the summer in the form of a seminar, maybe even working into some graduate coursework as well. This summer, we hosted, in partnership with a couple of the other interstellar groups that are out there, a student paper contest that challenged students across the world to answer the question, why human exploration of the outer solar system and onto the stars? And so we gave out some awards for that, and we've posted the winners on our website, and you can actually read their submissions there as well. So education outreach, we do want to talk with folks across the full spectrum, whether it's grade school or a physics colloquium. We're happy to support all different opportunities to engage through speaking engagements. If somebody has something that they want us to come support, you can just go through our website and we'll try and get you on the schedule and come support and chat with you. Now, just to talk a little bit about the internal R&D, I don't want to spend too much time on this. There's actually other stuff available on the web. I want to try and get to these proposals as soon as possible. Today's about the grants. But the haiku of what we're doing internally here, we going back to those 3 swim lanes that I showed you, we definitely, the work that we're focusing on internally fits in that rightmost category, breakthrough, if you will. We're working on the frontiers of physics, if you will, trying to develop that deeper understanding of how we might tie those 2 circles in the Venn diagram together. We're working on something we call a dynamic vacuum model. This is a non-local hidden variables type of physics model. You'll actually hear a talk today about another model that fits into that category, but we've been working with this for a while now. We're on a second DARPA grant. We had some successful work that we published in Physics Open, where we did a lot of numerical analysis of our physics models, modeling hydrogen, looking at the electron orbitals. We expanded that technique to look at molecular hydrogen. We've expanded that modeling approach to also consider the proton and beyond that. So I think that the takeaway of everything that we've looked at in terms of trying to think about a physical implication of the model is when we look at the dynamic vacuum model and we consider something like the Casimir cavity, we think that there is structure to the perturbed vacuum state that might exist in a Casimir cavity. And so you got a couple pictures up on the right-hand side there that kind of show some analysis results from our numeric world line algorithms that we use to go through and study how the vacuum energy density might vary within a Casimir cavity. In this case, this is like a little 4-micron Casimir cavity with a little pillar structure in the center. If you look at the little bottom thumbnails on my chart there, you've got some gold plates that are representative of cartoon representations of a Casimir cavity, and then there is a red fork, which is like a pillar structure we're trying to put inside to see if we can't measure this predicted structure, if you will. And so that's what some of the predicted spatial variation is that might exist in these cavities. And so the work that we're doing for DARPA right now is just to go see if we can measure the presence of this spatial variation in the quantum vacuum. So, and there's plenty of stuff to go look at online with that. If anyone has any questions, you can send me a note. I can send you some additional materials or links to videos where we talk in much more detail about that. External R&D, this is the purpose of what we're getting here. We're joining together for today is to talk about our Interstellar Initiative grants. part of what we want to do as we try and trace towards our pinnacle objective, we want to externally support research and development in the community. We want to, and we're doing this in a very tangible way. We've established this biennial grant process. So this is something we'll do every 2 years, where we try and fund a spectrum of research proposals for about a 12-month period of performance. And so by doing this every 2 years, very focused on power and propulsion, we hope to kind of grow and mature the capabilities of the research community and provide opportunities for folks, especially our 9 August folks that are with us, 9 proposals that are with us today. And in terms of what a grant might look like, we have 2 different categories. We have a tactical grant category, which is kind of maybe more in a theoretical focus, unless it happens to be part of a more mature research project. But that's capped by $100K maximum allowable award amount. And then we also have a strategic grant category, which is meant to potentially engage in a little bit more empirical effort, where we might sponsor some work getting conducted in a lab. Now, this is where we've got some great collaborations with Breakthrough. We've got some Breakthrough folks online today. Definitely want to say thank you to the Breakthrough team for supporting kind of working some of the mechanics here. And then Texas A&M is helping us with the contract initiation and administration. And so special thanks to all the extended team for everything they've done to help turn the wheels on the machine and keep things moving forward. So, and as part of conducting the I2 grants, we do want to have public engagement. Today is virtual, right? This kickoff meeting is virtual. We had hoped for this to be something that we could do in person and then also have a streaming aspect. If everything goes well, the midterm briefing will hopefully be face-to-face. We'll also host the streaming functionality so that people can view it virtually and then watch the proceedings later if they want. And ideally, the final briefing will allow us to be face-to-face. And in both cases, for the midterm and the final briefing, we'll potentially host those either in Houston and or at Texas A&M, where we might flip the locations between the two. So we'll just have to see how things go in terms of some of the boundary constraints that we have. As I move into the last slide here, just wanted to highlight the fact that LSI has some close collaborative relationships with some companies that fall into the commercial space category, and companies that fall into the commercial power category. Intuitive Machines, that's the one of the companies that has a commercial cargo to the lunar surface. We've got some good connections with them. Axiom Space, they have the commercial access to the International Space Station, and they'll be beginning building a independent space station, a commercial space station modules to go to the International Space Station. Switching into the power category, X Energy is a nuclear power company. They make nuclear fuels for nuclear reactors, and they also have nuclear reactor designs that they're working on. And then moving over into the fusion category, we have some connections with General Fusion as well. So that's, you kind of see commercial space and commercial power. We have some interesting threads that we can pull as opportunities come up in case somebody's interested or curious about trying to engage people with some, how do we take some of the things that we're talking about now? Can we learn from other folks that are doing things today that might have some proximity to what we're doing? So with that, that's all of my opening comments there. I think we're just a couple minutes ahead of schedule, so I will switch gears here and bring up the first set of charts here.
Sonny, do you want us to request remote control so we can move cursors and flip or not?
I will be your chart flipper. I will flip the charts for you. So I'll pull up your charts here, Phil. Okay. And go to full screen mode. And before you get started, the first talk we have here is the first proposal that we're going to hear from is Phil Lubin. This is his directed energy project. So I'm going to just hand the microphone over to Phil. Phil, thank you for joining us, and I'll change my background just to let you know when you're in your time frame. So you have the microphone, sir.
Okay, all right. First of all, I want to thank Limitless Space for putting on such an extraordinary event, as well as their generous support and their partners Breakthrough for making this happen. It's just a wonderful event. I want to try to convince you why directed energy, even if we had fission, fusion, and even other breakthrough technologies, is both synergistic with and a path that's unique, and why you'd want to do this in any case. So it is a path to truly long-term strategic transformation. I will, in the spirit of going incredibly fast, also go incredibly fast through these slides to give you a taste. Look at our website. We have more than 50 technical papers on our DE program. There's a TED Talk that appeared a couple weeks ago that I made, and find us on ResearchGate. Okay, next slide. So our team is fairly large. We have a quite ambitious directed energy group, along with many other astrophysics efforts. The people's names, most of you won't know. We have a number of research scientists, engineers, and students involved, including undergraduate students. I'll talk about that more later. Next. So directed energy propulsion is somewhat unique in that you don't take your power source with you. So just like the don't leave home without it, don't leave home with it. And you'll see why this is such a unique approach here. So there's many applications. On the left side, you see an artist's rendition of using directed energy to photoconvert on board and then drive an ion engine. This is useful for high mass missions to planets and the outer solar system, including human missions to Mars. And I'll explain why that's such a radical approach to getting to Mars. We have what we call Mars in a month, which is designed for cargo and humans. Then in the lower part of the left, you see the direct momentum transfer mode, where we can go to relativistic speeds for interstellar capability. Right-hand panel, just many of the different applications: Earth to Moon, point to point on the moon, moon to orbital craft, and then even to Mars. Okay, so next. There's a long-term plan that we have, and again, you can spend more time looking at this later. At the top, we have emerging technologies that we're trying to integrate into our kind of roadmap to the future. It starts on the left with laboratory demos in yellow, proceeds on to outdoor, then to ground to space test, Earth to Moon, power beaming for fast interplanetary missions, and then on to interstellar. And they all come from the same core technology. So there's emerging technologies, current technologies in green. The blue is the scale. We are completely scale, both independent and dependent, depending on the application. So we can go from things the size of your hand, which are useful on the moon for rover power transfer, to things the size of a small city, which are capable of both interstellar and rapid interplanetary, as well as other applications. And down at the bottom, we have the other applications: lunar point-to-point, high-speed laser comm, space debris mitigation, planetary defense, solar system-wide power, and LiDAR applications. Okay, next. The objectives of this 12-month program are further develop our laboratory tests and go to a sparse array, sparse phased array that I'll explain, construct 3 prototypes, and then vary the baseline between them. And that will become clear in a moment. Work on the design of a lunar payload. We've been talking to IM for a lunar beacon locking demonstration, and then look at other system designs for the next phase. Okay, next. So long-term program goals for the whole program are to develop directed energy for high-speed applications, enable relativistic flight for the first interstellar missions, enable rapid interplanetary missions, beam power for high-SP ion engine missions, and many, many other space applications. And I'll contrast this with chemistry, which unfortunately at 1 eV per bond, the efficiency is very small, of order 10⁻⁻10. Photonics is an exponential growth field, much like electronics, and it's reached the feasibility point for propulsion and large scale power. There's a lot of basic R&D that's involved. I'll explain more of that. It's not an all or nothing program. That's what's somewhat unique about this, is you can start with very small systems that are very practical and work your way up. And it leverages the large scale US and commercial and DoD interests in directed energy. Next. Okay, so this is sort of the potpourri of what you can do with propulsion, from chemistry at the bottom, nuclear thermal, working your way up to nuclear, which we'll hear a lot more about, into solar, and then finally at the top, directed energy. So I won't dwell on the others because you'll hear much more about those, but directed energy can operate in 2 modes. The top mode, where we have direct drive, uses direct momentum, photon momentum transfer to a reflector and then propels the reflector. That mode is the one which is uniquely capable of relativistic flight in this application. The second mode is to go to indirect drive, where you photoconvert and then drive a high performance ion engine. And I'll explain why those two, which use the same directed energy system, but have 2 different application spaces: direct drive for high speed, low mass, relativistic missions, the ion engine approach, indirect drive for high mass, rapid interplanetary missions. Next. Photonics is exponential. It's an exponential growth field. It's been growing for the last approximately 30 years with about a 20-month doubling time, much like Moore's law in electronics, driven by other factors having nothing to do with space, but having to do with consumer need for and industrial needs for photonics. Next. So the way that you make the system that we're talking about is by parallelization, not by building one gigantic laser. So we take actually a number of very small laser amplifiers. They're technically not lasers, but laser amplifiers. We run in what's known as a MOPA technology, topology, which is a master oscillator, which you can see the seed laser at the left. And then we amplify up and then do beam combining in free space. So there is no upper limit to the amount of power. Power is not the problem. Parallelizing and phase convergence, which is very much a mathematical problem, is the core of the issue. Our targets are cooperative, therefore we have a phase reference beacon on them, which is a critical difference between our approach and a tactical weapon system approach. Next. So this is just showing simulation data for rapid phase convergence. The time scale on the lower left image is in tens of microseconds. So a 1 there is 10 microseconds. Each phase is split out for the apertures, which will become clear in a moment. And you can see they phase out very rapidly, of order a few microseconds. And then on the right is the array power, which starts dephased and then rapidly goes to phase. So very high Strehl ratios very quickly. Next. 2 modes of operation, as I mentioned: direct drive, momentum transfer, and indirect drive to drive ion engines. And we'll see why these work so well synergistically for both low mass, high speed, high mass, lower speed. And lower speed is not slow, it's way faster than chemistry. Next. So this is just a little drawing of what we're building. The insert on the left is a 1 meter demonstrator. You know, it looks something like a rocket launcher. It's a photon launcher. And then the artist rendition on the right is how you might want to transfer power to assets in orbit or to the moon or for a relativistic mission. Okay, not an issue for space-based. For ground-based, we have to worry about the atmosphere. Space-based, we don't. Next. Okay, so this is showing 3 plots of speed on the left axis, speed divided by the speed of light on the right axis, or beta, as a function of array size from 1 meter to 10 kilometers for 3 different aperture fluxes of 1, 10, and 100 kilowatts per square meter. The purple lines are, the upper one is 10% the speed of light, next one is 1% going on down. So this is just showing for the left panel is for a 1 gram, so-called wafer scale spacecraft. The middle panel is for a kilogram, or like a CubeSat. And the right panel is for 100 kilograms, something like a Voyager class mission. In all cases, it's a scaling issue. You can get to any speed you want, up to close to the speed of light, just depending on the size of the array and the amount of power. And there's a whole trade-off. We have it discussed in great detail in our papers next. So this is a kind of a high-level rendition of where we are and where we're going. We're currently at phase 1, sort of meter scale, multi-kilowatt class systems. In about, our hope is within, say, 5 to 10 years, we'd like to be at a 10 to 30 meter class array to do some very useful beamed energy sail experiments. And then, you know, sort of the 20 to plus year time scale, we'd like to be able to build out to kilometers. That's very much dependent on 2 things, economics and technological development targeted at low cost, highly scalable modular systems. Next. So we were asked by NASA to look at, can we get rapidly to the outer solar system? In particular, is there a path to Mars in 30 days? So the answer is yes, there is a path to Mars in 30 days. It's difficult, but it's not impossible. The idea is to beam power to a spacecraft, reconvert on board, and then use a modest performance ion engine, ISP of between 3,000 and 10,000. That path actually can send humans to Mars and slow down. You don't have to have a beaming system on Mars to slow down. You can do it all from the Earth. There is a futuristic path, which I'll just mention. It's not something that we're working on seriously, but you could get to Mars in 2.5 days, including slowing down at 1G with direct photon drive. It requires vastly higher power levels than we're capable of currently, but it is something to think about, that there is a real physics path to Mars in 2.5 days. Next. So these are a number of missions that we studied, going from 25 kilograms to 40 tons delivered for the indirect drive mode, where we convert and then drive an ion engine. I'll draw your attention to the one at the bottom, which is a CubeSat flyby of Mars, a 120-day mission. If you notice the column marked delta, which is second from the right, is the size of the array. It is 10 meters. And the very right one, delta optical power, is the phased array power, which is a little over 1 megawatt. So this is a fairly low hanging fruit example of where we could go. Next. Okay, we've done a lot of laboratory demonstrations. This is a so-called Mach-Zehnder 2-element array that allows us to have extraordinarily long baseline tests, and I won't bore you with the details. See our papers next. Next, yes. Okay, so this is an example. That's fine too. This is an example of what our lab.
You need me to go back?
No, it's okay. This is an example of what our lab looks like. We have 8 labs. This is one of them. Lots of photonics, and it looks like a zoo, but it is the way that photonics is done currently. So we have a lot of infrastructure in place, which you'll see from the data in our papers. On the left, we actually run a high altitude observatory at 4 kilometers elevation, similar to Mauna Kea in altitude. Excellent seeing. It's a great test site for doing ground to space, ground to moon, ground to other spacecraft possibilities. So it's an excellent and unique site for us. We run the site and have for more than 20 years. Next. Okay, this is an actual 8-channel phased array on the optical bench. The picture you see on the right is not CGI. That's the phase lock beam pattern. It's a sparse array, so hence you have a lot of side lobing or grading lobes. Lots of widgets. Won't bother boring you with it, but it does work. Next. This is the same basic setup, except now we've allowed for atmospheric perturbations via a deformable mirror. So we can inject into our system atmospheric perturbations for ground-based systems. And this actually works surprisingly well. We've been able to take care of what we feel are reasonable atmospheric perturbations in this way using our beacon approach. Next. So we're building up a number of core subsystems. This is a 19-element array core, of which you would then array these to get larger systems. They're all identical. And so there they could be mass produced. This is about a ½ meter in size, so it's easy to work with. Next. This shows one of the sub-elements, which is about the size of your hand in diameter and about the length of your arm in length. It has all the electronics, photonics for the system that I showed you in the previous slide. It could be replicated for mass production. It's not what we would go for the very largest systems, but it's good for what we're doing right now. We'll be making 3 of these units for the Limitless Space program, and then I'll show you what we're going to do with them coming up next. We've done large baseline tests to see how well we can do, and the answer is we can do better than 1/100th of a wave at 11-kilometer radius, which is a 22-kilometer diameter array, which is just phenomenal, frankly. Did not think we could do this well. Next. We can do all kinds of custom beam patterns because we are essentially a Fourier transform device. We have control of the phase and amplitude if necessary, so we can create custom beam profiles. This is a helical phase on the left, which produces a beam profile which looks like a donut, as you see on the right. So we can produce anything. We can produce the logo for Limitless Space, for example, and write it on the moon. Next. Okay, next, please. So we're going to build 3 of these subsystems or subarrays, sub-elements, excuse me, and then put them on Azel mounts and then be able to run them at variable baselines with a beacon, as you see on the right, and the 3 elements on the left. And we can move them around and measure the beam pattern that comes from them. And I'll show you why this is so interesting in just a moment. So this is a very sparse array, but it actually tests essentially all of the critical elements of the system. Next. Okay, so this is speed versus mass. The speed goes as the -1/4 power of the mass of the spacecraft. So not as bad as you might think. If you increase the spacecraft's mass by a factor of 10,000, the speed only goes down by a factor of 10. So this just shows speed versus mass from a gram to 10 kilograms for relativistic missions. The middle dotted line is 10% speed of light. Next. If you want to send Amazon to Mars, it takes about 8 hours, including stopping. You do need one on Mars. If you want to send it to the moon, it takes about an hour. Okay, so there's a business model there somewhere. Next. Okay, so this is one of the things that I'd like you to kind of stare at this. Left is the IM Luna. It's the Nova-C, excuse me. The Nova-C lander, where we've outfitted with a phased array beacon, which you see is the red thing on the upper left, and then wide field infrared cameras. The 3 elements that I just showed you on the ground can transmit to the moon, and because it's a sparse array, they actually produce a series of spots. So we might want to write a children's book called How the Moon Got Its Spots. And the idea is that the Nova-C lander would provide the phasing beacon and also would record the target board, which is the moon itself, and we would produce these spot patterns. And again, we can do all kinds of neat things. This would be a fabulous both physics and demonstration of the program. And this is just with 3 elements, very modest on the Earth. Next. Okay, schedule. So we're almost, hopefully we'll get started in, November, December, something like that. So mostly focused on laboratory work and outdoor testing, and then some work on the lunar payload, which we think is a really critical element for the long term and a very practical thing to do. And then system design, software optimization, et cetera. A lot of mathematics goes into the phase convergence algorithm. Next. You can also use it to defend the planet. Not sure it's worth defending some days, but you might want to look at our papers on planetary defense, which uses similar technology, works incredibly well. Next. Conclusions. This is a path forward to propulsion transformation. Quite literally, it's a path forward to ultra high speed spacecraft. It's the only current way I know to get to relativistic flight. I'm hoping that we'll hear more about other possibilities today. There's many other space applications, molecular composition analysis, planetary defense, LIDAR, space debris mitigation, all kinds of laboratory things you can do too. We've been talking to people about extreme equation of state. Almost there. Heavily leverages the photonics and electronics industry, and we know how to get there. But what's critical is the actual long-term dedicated program. So we think that the US should help us lead. And next is last, which is that this is a fabulous way to attract both students and the public. We've had over 100 students in the last 5 years alone, about 300 students in the last 10 years work on directed energy. And it is truly a way to engage the public imagination. And as I said, I see this as a synergistic technology, not one that is exclusive of others, but is synergistic with nuclear, chemical, and any other technology. Okay, I'll stop there.
Thanks, Phil. Appreciate it.
Yep.
Fantastic talk. Enjoyed that. For folks that have any questions, remember we'll have a dedicated Q&A session after this, the first 4 talks this morning. So just hold on to your questions until then, and we'll come back to them at that point. Let me pull up the next presentation here real quick. So again, thank you, Phil.
Welcome.
Next up, we have Ray Sedwick will be talking to us. Let me pull up his charts here. He's got a direct drive fusion concept. So if you remember my 3 swim lanes, he is in the middle swim lane, and he is the direct drive fusion approach. He's joining us from University of Maryland. Ray, can you see your charts?
I can. Can you hear me okay?
I can hear you good.
Okay.
You have the microphone, sir.
All right, thank you. So let me just begin by also thanking Limitless Space Institute for providing the funding for this project. As Sunny mentioned, so we're on a tactical grant. So this is early stage looking into this concept. I'll be discussing the centrifugal confinement direct drive fusion propulsion. I wanted to mention the contributors to this presentation. By and large, most of the presentation came from other folks that have actually been working on the confinement concept for a couple of decades. And so I'm sort of more recent into this particular technology, as we have an interest in taking the confinement technology and transitioning it to this direct drive fusion propulsion system. So next slide. So just a quick outline. So we'll start and talk a little bit about the value proposition and the mission drivers for a system like this. I'll talk, most of the talk will be about the confinement technology itself. So I'll show some simulations and hardware demonstrations that have been done here at the University of Maryland. Talk about how we're looking to transition this to a direct drive concept for space exploration. And then briefly just talk about what the path forward is going to be. Next slide. So some of the mission drivers, so just as a reference, a couple of years ago, NASA had a solicitation where they were looking for some technology development, and they provided some reference missions for deep space exploration. These particular missions are maybe a little bit pedestrian with regard to what Limitless Space is really looking for, but it provided sort of a nice baseline to get an idea about what some of the operational requirements would be for a system. And so the 4 missions that were sort of baseline, so a 45-day trip to 1.5 AU, so that's a Mars mission, 1 year or 1.5 years to 5 AU, so that'd be a Jupiter type mission, or 5 years out to 40 AU. And so we show just sort of representation of what the approximate delta V for a mission like that would be. the power plant power that would be required, thrust levels based on sort of a baseline architecture that we use for reference, and then what the required specific impulse and specific mass would be for such systems. So sort of the takeaway from this is that the thrust, the specific impulse, and the specific mass values for systems like this really favor something that's along the lines of a direct drive fusion type device. Next slide. So what is centrifugal confinement? So fundamentally, it's a magnetic mirror, if you're familiar with different fusion confinement technologies. Sort of the difference is that in addition to the magnetic mirror, there's a radially applied electric field. And this field, the E cross B, causes a rotation of the plasma. You can have the E field pointing either radially outward or radially inward. There are actually some reasons why it might be advantageous to have it pointing radially inward, which is exactly opposite to what's shown in the figure there. Also key is that the ends have to be electrically insulated. If this is done in a laboratory in a confined sense, less of an issue if you're doing this in space. That's important because you have to maintain an electric potential across the field lines, and so they can't short out at the end. So the centrifugal acceleration then pulls the plasma away from the center line towards the midplane. And so the gray areas show sort of notionally where the plasma would exist. And so that helps to improve the actual confinement beyond just a simple mirror machine. So in the rotational direction, there is a shear, so it doesn't rotate as a rigid rotor. And this shearing mechanism actually helps to stabilize a variety of the plasma instabilities that would otherwise be present if this was a pure magnetic mirror device. Next slide. So some advantages. So as I mentioned, there is a tendency that's been observed both in simulation and in experiment to suppress some of the natural MHD instabilities that occur in a mirror confinement device like this. It appears to help suppress microturbulence, and so that means that we would experience more of a classical cross-field transport, which is important for keeping the plasma confined. The coil design, because it's an axial device, is relatively simple in comparison to something like a tokamak. The rotation of the plasma and the shearing provides a direct viscous heating of the plasma. The thermal confinement time of the system is really established by the parallel electron transport along the field lines, but the electrons are also confined by the ion space charge. And so they're, because they're such a low mass, they're less susceptible directly to the centrifugal rotation. But if we confine the ions, then the electric field established between the ions and the electrons helps to keep the electrons in the system. And sort of a 0D analysis demonstrates that the Lawson criterion for confinement can be established at a rotational Mach number of around 4 or 5. The catch is that the electrical power recirculation is still required to drive this plasma in rotation. So there needs to be not a large, but a not insignificant amount of recirculating power that needs to be handled by the system. Next slide. So here demonstrate some other simulations that were done by a colleague. So these were used to actually demonstrate the suppression of the flute instabilities or the Rayleigh-Taylor instability. So to sort of read what's going on here, at time t equals 0, the system was actually in steady state, and there was a velocity shear. I should point out that we're looking end-on into a cylindrical confinement where we're looking at just a sector of the flow. At time t equals 0, the shear and the velocity was present, and the system had reached steady state. But then to demonstrate that shear velocity was actually stabilizing the flow, the shear component was turned off at time t equals 0 after having reached steady state. And then the system evolved as a rigid rotor into the future. And so you can see that within a few set delta t's, that the typical instability starts to grow. So this is a demonstration that the model was both capturing the growth of these natural instabilities and that the shear velocity component was actually stabilizing. Okay, next slide. So this was another simulation that was done. So this was a particle simulation rather than a fluid simulation. So this was done to also show sort of the ion confinement in the system. The particle simulation was done to account for large Larmor motion that might actually be seen to invalidate the MHD analysis. So on the right there, the two examples that are shown are both for a mirror ratio of 7 and rotating at 2 different Mach numbers. So the way to read the plots here is the horizontal axis is the parallel component of the velocity and the vertical axis is the perpendicular component. And so this shows sort of a representation of the instantaneous distribution function of the particles within the system. So at Mach 3, you can see that there is pretty significant amount of loss cone removal. So those sort of faint gray lines going up to the left and to the right represent the boundaries of the loss cone. So any particles that appear below that boundary are lost from the system or will rapidly be lost from the system. And then at a rotational Mach number of 6, you can see that you have almost complete elimination of those particles from the loss cone. So this demonstrates that it does indeed achieve the improved confinement against just a simple magnetic mirror operating at the same mirror ratio. On the plot here, V equal to 1 corresponds to about 12 keV of energy for the particles. And so sort of the takeaway from here is we sort of have 2 knobs to turn now. We have both the mirror ratio and the azimuthal velocity, and the azimuthal velocity is a function of the applied radial potential. So we have 2 mechanisms to limit or to fine tune the control of the loss of alphas from the system. Next slide. So there was also a hardware experiment that was conducted at the University of Maryland over about a decade from 2000 to 2010. So this is just a diagram, schematic showing the configuration. So it was a long, slender geometry with a higher field region on the ends, represented with the red magnets, and then the lower field region in the center. The mirror ratio operated at about 9. The density inside was about 10 to the 20, and it was, for the most part, fully ionized. The ion temperature ranged from 20 to 50 EV. The voltage of the bank that supplied the E cross B rotation could be ranged from about 5 to 20 kilovolts, and the pulses, so it operated as a pulse system to keep the magnets from overheating. So the pulses were relatively short, about 1 to 10 milliseconds, but we'll see that that's long enough to actually achieve steady state in the plasma. And they demonstrated rotational velocities of about 100 kilometers per second. So there were 3 goals in this experiment, and I'll talk about those. So next slide. So the first goal was to actually demonstrate the supersonic rotation. So this was done by measuring the actual rotational speed directly using a 5-chord Doppler interferometer. And these measurements were taken about 550 microseconds, or about half a millisecond into the discharge. And so based on the data that's shown here, you can see that in the upper port that was looking at the motion of the plasma above the center line, the measurement showed about 90 plus or minus 5 kilometers per second. And through the lower port, you saw a rotation of about 60 plus or minus 5 kilometers per second. And so this demonstrated that during the discharge, you do indeed get a rotation of the plasma as expected. The ion temperatures are measured at about 40 EV, and they achieve rotational Mach numbers in the range of about 1 to 3 from this experiment. Next slide. The second thing that was important to demonstrate in the experiment was MHD stability. And so for reference, the time scale for the plasma to destabilize is on the order of about 2 to 20 microseconds. And so on the plot on the right, which is a plot of the load voltage versus time, So you can see on the bottom of the scale, the full scale of the discharge is only about 5 milliseconds. And the time scale for the MHD instabilities to arise is shown, almost as an unobservable, pair of vertical lines. And so this demonstrates that the plasma was seen to be stable over a very large number, thousands of MHD instability times, which sort of supports the idea that the plasma was actually operating in a stable mode. Also shown was the timescale for the momentum confinement, and that basically means that if you were to crowbar the system, how long does the system take to stop rotating? And so it's just a relative timescale that's shown there. So this provides pretty strong evidence that the shearing effect does indeed stabilize the instabilities that you would expect to see. Next slide. So the last goal was to demonstrate the centrifugal confinement. And so look below the diagonal dotted line. So what was done here is that chord-wise interferometry was used at the midplane and near the end to measure the density of the plasma, both near the center line and away from the center line. So on the bottom left, for a mirror ratio of 2, you can see that, so the black line in the plot represents the measurement of the density near the center line of the device, and the red line represents the density farther radially outwards at about 15 centimeters. And so you can see at the lower mirror ratio, there's a higher density along the center line and towards the outer radius, as one might expect. And then at the higher mirror ratio on the upper right, you can see that there's a switch of the densities. And so the density out at the 15 centimeter radius as compared to along the center line is greater by a factor of about 12. Right? So this demonstrates that the plasma is indeed shifting away from the ends of the device and closer to the midplane during operation. Next slide. So some preliminary work was actually done with regard to how one might turn this into a thruster. And so sort of the obvious thing to do is to simply introduce an asymmetry in the field to allow plasma loss on one end, or a greater plasma loss on one end. And so for this particular simulation, it assumed a volume of about 1 cubic meter, density of about 10 to the 20 per cubic meter, and confinement time of about 2 milliseconds. So assuming a mass flow rate of 2 times 10 to the minus 6 kilograms per second, the simulation demonstrated a specific impulse of just under 1 million seconds, which is sort of to be expected. The thrust generated was on the order of 10 newtons, and the jet power was about 25 megawatts. So the power level for this is actually consistent with the fast Mars reference mission from my first slide, but the thrust is about 60 times too low, and the ISP is actually about 60 times too high for the optimal system configuration for that mission. So the power is about right, but the thrust and the ISP aren't really where you would like them to be ideally. So next slide. So one of the sort of main innovations beyond just the baseline confinement technology that we're looking to implement is this notion of a bypass flow. So the whole reactor that we've been talking about thus far is sort of over on the left in the blue highlight. So you can see the central electrode, but the idea is that because the plasma is confined away from the center line, then down sort of internally to that electrode, we can introduce a bypass flow of some other type of propellant. And then at the exit, that propellant would mix with the energetic alpha particles that are being allowed to leak out of the reactor. These would then mix and then expand through a magnetic nozzle. And the idea is that we're energizing the bypass flow to bring it up to the energies that are desirable to reduce the specific impulse and increase the thrust of the system. And so we would have a knob to turn that for a fixed power output, we can sort of tune the amount of thrust and specific impulse that the system could actually provide. And next slide. All right, so the path forward in the longer term, so sort of the schematic of the device that is shown here. So basically what we're looking to tackle is essentially all of the engineering to make a system like this feasible. Sort of the fundamental physics, I think, has been demonstrated, not that there aren't still some questions that need to be answered there as well. So at sort of the system design level, we have to investigate the flow mixing of the bypass flow propellant, the effectiveness of that, and what sort of exit conditions we can actually achieve. We're interested in using common bypass flows. So by common, I mean readily available throughout the solar system. And so water would be a great option for the bypass flow. It doesn't really matter what we use, because it's not actually going, it's not in the reactor, it's sort of flowing down the center line of the reactor, but it's the system is sort of agnostic to what we might use for our propellant. We're interested in using direct power generation on the upstream end. So we don't want to heat something and then convert that power thermodynamically, because that means that we have to have big radiators. And so we're baselining what we call the standing wave direct energy conversion system. You may or may not be familiar with a cousin of this, the traveling wave direct energy conversion system. You can basically think of this as a linear accelerator working in reverse. So rather than using RF signal to accelerate ions, you're decelerating the ions against an RF signal, and you're extracting the kinetic energy from them. And so we've done actually some research of that in the past and demonstrated really good potential conversion efficiencies with a system like that. We have to recirculate the power at a very high voltage into the system. So we're talking about megavolt type voltage levels back into the system. And so we're looking at possibly integrating something like a Cockcroft-Walton charge pump, which would actually couple very nicely to the RF system. Of course, there's the structure, the magnets, the shielding, so on and so on. There's all sorts of technology sort of hurdles that have to be overcome. And so the near-term goal is system sizing. So what is the power to mass scaling laws for the system? Next slide. So this is the schedule. So they mentioned sort of the 4 areas. So E and B field geometries, assessing the confinement and the alpha moderation, analyzing the exhaust and bypass flow mixing, and then looking at designs for the power conversion and recirculation. Next slide. So this is the team. So myself, my colleague, Professor Adil Hassam in the physics department. He's really the one that's been really pushing this technology for the last couple of decades. And then 3 students currently working on it, Jerry Carson, who's also a full-time employee of APL, Ella Vicente, who's an MS, soon to be a PhD candidate, and then Amelia Sherian, who's a senior honor student in the department. Next slide. So with that, I'm done, and I guess we're going to push questions to the general Q&A session later. All right, thanks for your time.
Thanks, Ray. Great talk. I appreciate that. We'll go ahead and jump to the next presentation. Just a quick reminder, if you have questions that come up, instead of putting them in the chat, try and put them in the Q&A panel. We'll try and catch questions wherever they get put in, but we're primarily monitoring the Q&A window, but we'll try and catch anything that is over in the chat. So, and again, we'll have time for questions here in about another 40 minutes after the next 2 presentations. So next up, we have Jason Cassibry from University of Alabama, Huntsville. Pull up your charts here, Jason.
Might help if I unmute myself.
Yeah, so we have Jason Cassibry and Gabe Zhu to talk to us about another fusion concept. So this is fusion concept number 2 for the day. I'll hand it over to you, Jason. You have the con. Let me clear my little red alert thing here. There you go.
All right. Thank you very much, Sonny, for the introduction, and also to Limitless Space for the wonderful opportunity. It's an honor to be a part of this this group. So our title of our talk and our work here is Exploration of Pulsed Break-Even Fusion at 100 kilojoules energy for breakthrough propulsion. I'd like to acknowledge our team members here, Dr. Gabe Zhu, a professor at University of Alabama at Huntsville, Sumatro Sinha, And in no particular order, I'd also like to acknowledge the wonderful body of students that we have working on either the laboratory or modeling. And so in no particular order, and pardon me for taking a moment to do this, Bailey Gregory, Jacob Kinsey, Logan Curtis, Nash Beasley, Shelby Westrich, Bennett Hasner, Mason Davis, halfway through, sorry, Michael Canary, Alat Vyas, Nathan Schilling, Pankrit Darkhorn, who prefers Boom, Brian Winterling, Suraj Kumar, Brian Taylor. And if I forgot somebody, I'm very sorry. So let's go ahead and move to the next slide, please. So the objectives of this particular program are first to develop scaling laws for solid state fusion targets for pulsed Z-pinch fusion based on rising currents. And so I can field questions on why we're interested in rising currents specifically a little bit later. The design of the targets to achieve tailorable ion densities near 10 to the 26 to 10 to the 28 cubic meters at peak current. We'll show you why in a little bit. And achieve validated simulations in our 3D SPF Max computational tool against experimental data to determine scaling laws and target variations to achieve ignitions at what we hope could be achieved with sub-megajoule energies. Next slide, please. So just to orient you on the parameter space for nuclear technologies and why they can kind of help get us to the outer planets and to do interstellar precursors. So I'll orient you with this chart here. So the y-axis on the chart to the right represents the delta V of the spacecraft, basically just the change in velocity needed to do a particular mission. And corresponding to that, you have the specific impulse on the right-hand side to roughly achieve that. The horizontal dashed lines represent different missions of interest. And as you go vertically on this chart, the missions get harder and harder to do, and they start to exclude more and more technologies and limit it to fewer. So on the left at the lower right, we have the lunar round trip in a week. Well, we can do that mission, or at least we could 50 years ago, and hopefully we'll be able to do it again very soon. And we can do that with chemical. And a Mars round trip, you can see the x-axis there is energy density. And so chemical can store about maybe 10 to 50 megajoules per kilogram. And it starts to limit what you can achieve with specific impulse. And so Mars round trip in 2 years is about all you can do.
I didn't want a lot of.
I'm sorry, what?
So somebody was off mute. Go ahead, Jason.
Oh, okay, sure. But as you push out to the outer planets and you start looking at things like, for example, a Titan sample return mission, heliopause flyby, a Oort cloud, those things get tougher and tougher, and you can see the required energy density starts to push out to 10 to the 12 to 10 to the 14 joules per kilogram. And then there's this huge gap where you start to look at interstellar precursor missions. And really, it's stretching the limits of even fission and fusion to do that. A multi-stage mission could be accomplished in maybe 40 or 50 years. And really, it starts to become the realm of antimatter, or if they can achieve these goals, it's really exciting that we have folks like Dr. Lubin working on beamed energy, which could also potentially achieve an equivalent to energy density. It's not really the same because they're transferring their power. But anyway, let's go to the next slide, please. So if we advance one more, this will animate and kind of show you what the energy densities are of these different reactions. Advance one more time, please. There we go. So again, advanced chemical, about 50 megajoules per kilogram. Electric still needs onboard power. So if you have indirect drive with either fusion or fission, you have a power conversion efficiency loss. And so it really makes the specific power tough. Nuclear fission, fusion, and antimatter are the only things in terms of onboard energy storage that really give you 10 to the 14 to 10 to the 16 joules per kilogram to achieve these missions if your power reactor is on board with you. Next slide, please. So what is fusion? This is what we're going to be doing. So fusion is basically the merging of the light isotopes such as deuterium and tritium. And what they do is they form high kinetic energy particles such as a neutron and helium. So most of the energy goes into the kinetic energy, and the energy is derived from the residual strong force of the binding of the nucleus of the elements. Next slide, please. The work that we're doing here, I want to acknowledge, is an outgrowth and is derivative of a broader effort going on at NASA Marshall, led by Dr. Rob Adams, called the pulsed fission fusion hybrid concept. So we're looking at a spectrum of technologies to enable advanced propulsion, from pure fission to pure fusion and everything in between, where we're looking at the detonation of different types of what we call targets. That's the fuel pellets that are expelled at the nozzle. Next slide. And this is one of the vehicle design concepts. This is a Mars vehicle. Next slide, please. So the missions that we're interested in, of course, Mars and Jupiter and Saturn, but really, if you start to look at things like a round trip time to Neptune in just a few years, that really starts to be the realm of nuclear or beamed energy, or these more exotic things which are being developed by groups like this Limitless Space Institute Opportunity. And so what you see here is a panel of 4 charts. Initial vehicle mass in low Earth orbit, which in every case we try to pick something less than 100 metric tons. It gives you the rough thrust at the corresponding design point, the required specific impulse and jet power. And the takeaway here is you can do a round trip in 4 years with fusion or a fission fusion hybrid concept that's open cycle with a specific power of about 20 kilowatts per kilogram. Now, if you become more ambitious and we start to get closer and closer to these interstellar relevant missions, next chart, please. You start to need a maturation of this technology to maybe something like 5 kilowatts per kilogram for a gravitational lensing experiment. So if you can take your vehicle out to about 550 AU, and you're going in the opposite direction of the thing that you're interested in imaging with respect to the sun, you can start to do some really exciting telescope work using the sun as your lens. Next chart, please. If we push out even further, Proxima Centauri, for example, has a potentially habitable planet. And here you would need, for fusion, a single stage is going to take you 2 centuries to get there, even with a 25 kilowatt per kilogram. But you can get that time down if you have maybe a 5 or 6 stage system. I personally hate the thought of throwing away a perfectly good reactor, since we don't have one breaking even yet. But it really does start to push the limits, but it is possible to get there in less than 2 centuries, and actually less than 1 century if you start to multi-stage it. Next chart, please. So where might we going in the next century if we develop some of these technologies? We have quite a few potentially habitable planets that we know about. If you advance once, it'll animate and give us nice pictures of what we think some of these planets look like. So we have Earth, we have Proxima Centauri, Wolf 1061c, Gliese 667c, GJ 357, and that's basically the planet Vulcan 40 Eridani, all with about the same size as Earth. The temperatures are potentially very habitable. Some are a little colder, some a little hotter, but it's very exciting considering that within 20 to 30 light years away, we have so many planets that we know of that are potentially habitable. Next chart. Now, this is the heart and soul of the presentation, or this sequence of charts. Let me orient you. On the left-hand side, we have a power balance chart. The single cyan dashed contour represents the boundary between, is it going to ignite and burn, or is it going to quench and cool off? As you know, we're all very good as fusion scientists at finding the space where fusion plasma quenches and doesn't break even. And it's very, very hard to get to that ignition space. On the right-hand side, we're going to look at this a little bit later, represents a color map of the energy, the thermal energy in that plasma. And the boundary where it breaks even and ignites is shown for reference. So you can see this is a pure inertial confinement concept, just showing how hard it is to ignite a deuterium plasma. This is a deuterium plasma calculation. You need a couple of times solid density deuterium in order to burn it. Next chart, please. Now, as you turn up a knob here and start to have an implosion velocity, this is just 100 meters a second. You see there's a new region that forms on the left-hand side, but at very, very low density. So your confinement time is seconds, if not minutes, at those very low densities. Next chart. We increase the implosion velocity. We might as well increase another one. You can see that this region starts to grow. Next chart, please. So we're just going up orders of magnitude. It's 10 kilometers a second. If you do it again, 100 kilometers a second, starts to become very interesting, because you can see now there's this new region that starts to grow. And in fact, if you were to continue to say 300 kilometers a second, that's basically where the laser fusion operates. And that's fine. If you advance to the next chart, we want to back off to something that we think we can achieve in this program, which is a 20 kilometer per second implosion velocity. That's pulse power 101 to achieve velocities like that. And so now we're at 10 kiloamps. And so now what we want to do is show you what happens when you start to include a strong magnetic field in this pulse. Next chart, please. So if we crank up to 100 kiloamps, this is very easy to achieve in our pulse power bank. You see that this region starts to grow because you're suppressing cross-field thermal conduction and you're adding ohmic heating into the system. Next chart, please. Now at a mega amp, which is about 3 times beyond our range that we can achieve, you see that this ignition region starts to really close up. And if we took it to 10 mega amps, next chart, now we have this very interesting region where you can find a path to ignition. It's just really hard to get to 10 mega amps. It's a very messy experiment. But it does open up the parameter space, but it also shows you there's this performance cliff right at 10 to the 27 to 10 to the 28 meters cubed. So while we may have targets that start at 10 to the 28 or so at solid density, we actually want to expand that plasma a little bit in order to get it lower so that we have a path to heat the plasma up into the ignition region. Next chart, please. So our goal, not in this program, but in a follow-on, is to get a 3 mega amp device, because this seems to be at the ragged edge of something where we have a manageable current, because 100 kiloamps is an extremely violent reaction. But if you look now over at the energy plot on the right-hand side, the thermal energy of say 10 to the 26 to 10 to the 27, where your confinement time is 100 nanoseconds to a microsecond, the thermal energy is a very manageable amount of the order of tens of kilojoules up to about a megajoule. And so this would result in a much smaller reactor than a lot of the concepts that we've explored thus far. So we're trying to find that space and trying to get to that space. And the experiments that we get to do as part of this program will allow us to do some subscale relevant tests to figure out how we can actually get there. Next chart, please. So some of the modeling that we have done recently includes looking at how you would turn this into a propulsion concept. And so this is just an animation, and this very non-intuitive wrapping, the copper wires there represent a magnetic field windings in a longitudinal sense that create an azimuthal field, which shows promise for really good propulsion. If you go to the next chart, we're working with some collaborators, Dr. Steve Howe and Rob Adams, again, on different nozzle concepts for his pulse plasma rocket, which is within the family of things that we're looking at. His is a pure fission concept, and there is a thermal expansion of just pure tungsten. We're not allowed to do pure uranium simulations for obvious reasons. So we use tungsten as a surrogate for that. Next chart, please. Here are some of our team members. Dr. Gabe Hsu over there on the right-hand side. That good-looking gentleman in the middle there is Mr. Alan Davis. He is a former Apollo technician, and he's just with us as a love of labor. That man is 84 years old and comes to the lab just about every day. He's terrific. He's taught us a tremendous amount of practical knowledge about how to put hardware together, how to troubleshoot things. And then the lower right, that is I'm sorry, just having a brain fart all of a sudden. Anyway, let's move on to the next chart and talk about the milestones of the program. So we want to demonstrate an inert target shot with successfully triggered framing camera, optical emission, and pulse power diagnostics, demonstrate lithium deuteride fused target and confirm the neutron yield with time of flight neutron spectroscopy. That's something we're going to try to get done by about March, and conduct neutron yield scaling laws as a function of target mass changing voltage, and then 3D modeling and validation and development of scaling laws towards the end of the program in July, midsummer. And finally, complete the mission analysis for outer planetary interstellar precursor and interstellar flyby missions by August. Next chart, please. And Sumantro Sinha. I'm sorry, Sumantro, for that. Is his name. The schedule for the phase 2 program is listed here, and this is just kind of a reflection of the milestones. There's no need to labor through all of the fine points here. Next chart, please. Some of the diagnostics that we've put together for this, we have BDOT probes and high voltage probes, and these are just some illustrations of those. The chart in the middle under the word diagnostics, you can see one of our BDOT probes is just a nylon bolt in which we've taken magnetic wire to wrap around the threads, and that gives us a very consistent way of making those probes. And on the right there, we have a pulse power machine, which is not used in this program, but was used to help shake out the diagnostics to show the comparison between a simulated and the measured current, which we can get just to show that we can calibrate those measurements. And then over on the very left-hand side, that is a neutron scintillator probe, which we would use 2 of those to do time of flight to figure out what the spectrum is of the neutrons, which we expect to mostly just be 2.4 MeV DD neutrons. Next chart, please. So one of the critical things in this program is determining the density and the temperature of the plasma during the implosion process. And so for that, we have fast framing camera, and we also have this passive optical emission diagnostic from Dr. Gabe Xu, in which we're going to use spectral intensity and broadening in order to determine electron density and temperature as a function of time. Next chart, please. And in conclusion here, so the fusion concepts that we're looking at, we endeavor to enable rapid interplanetary space for human piloted and science missions and interstellar precursor missions. We're very excited about doing this, and we're very honored. The proposed concept is to explore neutron yield versus peak current, relying on the stability of Z-pinches during the first quarter period of an RLC circuit. Glad to follow up with questions if they come up during the panel discussion, the Q&A. The scaling laws will be developed from experiments and validated against our code, and then extended for a break-even concept, which we think can occur around a 3 megaamp current. And then the primary objective is to find a sub-megajoule path to break-even fusion to lower the cost and lower the size, and try to simplify fusion as much as we possibly can. So thank you very much. That was just a backup slide for Dr. Xu's diagnostics. And while we're switching over again, Sumantro, my apologies. I kept thinking Saroj Kumar, and I could not get Saroj's name out of my head for some reason. Anyway, very sorry about that.
Yeah, no worries, no worries. Sorry, I was on mute chatting away. Quick question for you. What was the name of the gentleman that you said it was 84?
His name is Alan Davis.
Alan Davis. Boy, I hope I'm so productive at the age of 84. It's really neat to see people, just continue to be interested and challenge themselves and trying to help push back the darkness, right? This is, I think sometimes maybe we should remember that sometimes challenges require multi-generational effort to accomplish. So it's neat to see that. So
he really serves as an inspiration for all of us. And I hope that I hope that I have that same gear when I'm that age.
Right. I was going to say, that's fantastic. All righty. Thank you, Jason. Appreciate it. Next up, to finish up the early morning session, we have John Bush from MIT. John, let me pull up your charts real quick. I see that you're off mute, so that's good. And I think I have your latest charts here. John Bush is going to be talking to us about some of the work that he's doing, developing a hydrodynamic quantum field theory. This is something that would potentially try and maybe increase the diameter of that circle of quantum mechanics, providing some additional insights. And so he's going to talk to us about that today. John?
Indeed. Thank you. If you want to go into full screen, yeah, great. So I'd like to begin by thanking LSI and Sunny in particular for the financial support and the organizational efforts in arranging this meeting. I should have put the National Science Foundation also on my front slide, as they've been supporting all of my work on this subject to date. So please proceed. Right. So as we all know, quantum mechanics is a theory that describes the statistics of microscopic particles, but doesn't describe their trajectories. And at worst, they actually deny that these trajectories exist. So the sort of canonical description of the free particle in quantum mechanics, you simply associate an energy and a momentum with that particle. But of course, as an undergraduate, one is left asking, but where is the particle and why does it move? So these are very fundamental questions that we believe we have some insight on coming from an unlikely source. And of course, the problem with this purely statistical description of quantum mechanics is it has introduced sort of proliferation of quantum interpretations, paradoxes, and troubling language, which we, again, think we've made some inroads on unraveling. So please, next slide. Okay, so hidden variables are theories that attempt to describe the underlying dynamics beneath the quantum statistics. So it would be a theory for particle trajectories, and the great majority of involved particles interacting with a wave field. So in particular, and of the sort of physical picture invoked by this hydrodynamic system, which I'll be describing, is the pilot wave theory of de Broglie, which involved a particle interacting with its own wave field, so basically generating its own pilot wave and then moving in resonance with that wave. And this was the basis of the original derivation of P equals h bar k, and which prompted the development of Schrodinger's equation and so forth. So that was the sort of classical pilot wave theory. Then there was a sort of variant developed more recently by David Bohm, which we find sort of not as satisfactory as de Broglie's original physical picture. And then there's been stochastic dynamics, which was developed by Nelson, where you can view the sort of you can try and rationalize the statistical behavior of quantum systems in terms of a diffusive process, so a particle moving with a diffusivity prescribed by the ratio of h bar divided by the particle mass. And this, I would say, Delapegne and Cheto have developed stochastic electrodynamics, which is sort of a modern extension of de Broglie's mechanics informed by Nelson's, and we'll come to that again in a moment. Next, please. Okay, so hydrodynamic quantum analogs have followed from a discovery made 15 years ago by Yves Couder and Emmanuel Faure in Paris. So they discovered a hydrodynamic pilot wave system where a drop levitates on a vibrating bath and self-propels, and it's dressed with a quasi-monochromatic wave field. And this really represents the first macroscopic realization of the sort of pilot wave theory proposed by de Broglie. And lo and behold, it exhibits several features of quantum systems, which were thought previously to be exclusive to the microscopic realm. So as Sunny said, this is now we have the intrusion of classical physics into quantum mechanics. So the Venn diagrams are no longer distinct. One intrudes into the other, and we're getting more and more intrusions. And the farther we go, the more quantum features we can rationalize. Okay, so the questions raised by this new field are, what are the key dynamical features responsible for the quantum-like behavior? And this we really know. You need a resonance condition between the particle and the wave, and you need the particle, the wave dressing the particle to basically be monochromatic. Okay, and so what are the potential limitations of this hydrodynamic system as a quantum analog? So we're coming to grips with that, but currently growing the grocery list of analogs. The last question, which we'll touch a little bit upon at the end of the talk, is, can this guide us towards a rational theory for quantum dynamics? So this is sort of in its infancy, but I think it's an exciting direction to pursue. So it's basically trying to complete a description of quantum dynamics informed by this hydrodynamic system. Next slide. Okay, so the hydrodynamic system is as follows. You have a vibrating bath. You can do this on a loudspeaker. It's vibrating about 50 hertz. You put a millimetric drop on it, and it's levitated by virtue of the fact that the air layer between the drop and the bath doesn't have time to drain during impact. And so this drop is then propelled along the surface of the bath, okay? And as you can see, it's sort of dressed in this monochromatic wave field. The wave length of that wave field is the Faraday wavelength. We can cycle that through again. And that's prescribed by the vibrational frequency, okay? And so you're below the Faraday threshold is the if you vibrate a layer of fluid, then the Faraday threshold is the critical acceleration at which you excite waves everywhere. We're below that threshold here. So in the absence of the drop, there would be no waves. So but the drop is basically moving on its own wave field. So it's basically creating its own potential and moving in response to it. And we've done the stability analysis saying when will a bouncing drop turn into a walking drop? And so all of this is out in the literature. And the key features, again, are the resonance condition. Without the resonance condition, you wouldn't get a monochromatic wave field. And the other, the other key feature is the notion of memory. So this particle, this object we call a walker. So it's not just a drop, it's not just a particle. Without the particle, there would be no wave. Without the wave, the particle wouldn't move. This system is, the key critical feature is it's non-Markovian. That is to say, it has a history. These are called hereditary systems. So if you have because this particle is moving in response to its wave field, the instantaneous force acting on it during impact depends on its history, because its history determines the local form of the wave field. And it's this hereditary nature of the system which accounts for the non-local features. So it's temporally non-local by virtue of its history, and this gives rise to effects which appear to be spatially non-local in the quantum sense. And so again, this system was discovered in 2005. I wrote a review of it in 2015, and if you want the latest version, I just finished something with my former graduate student Anand Oza for reports on progress in physics, and that's in press now, and that's a 72-page beast. So if anyone would like it, I'll be happy to send it to you. But next slide. So that has a really complete review of the subject. Okay, so I just want to show you a couple of reviews. This is a couple of examples of hydrodynamic quantum analogs. This is my entree into the problem. This is the quantum corral. So the quantum corral, you have electrons zipping around on the surface of metal, and they're contained by these positive atoms, which serve as the fence on the corral. And so they whip around, and sure enough, you get this PDF, which whose form you can predict with Schrodinger's equation. And of course, that's their complete description of the system. There's no notion of particle trajectory required. So I thought, oh, well, can we do this with walking drops? So next slide. So here we have a drop walking in a circular corral. So it's basically, it's prevented from escaping, and we color code the trajectory according to speed. So it's moving around in a sort of a random walk, and you think, we're not going to get anything coherent here. But you let it run and run and run. And sure enough, in the fullness of time, there's a correlation between position and speed. And as a result, you get an emergent statistical pattern, which is remarkably similar to that arising in quantum systems. Next slide. So again, we see that this sort of quantum behavior is not inconsistent with the notion of particle trajectories. And in fact, one could predict the form of the statistics simply by looking at the wave modes of the cavity. Okay, next slide. So the sort of physical picture is that of 3 timescales. So you have the fast timescale, which is the timescale of the drop bouncing, and this is responsible for the wave generation. Then if you strobe this dynamics, you see the particle just gliding along the surface with a monochromatic wave field, and then you have the emergence of a long-term statistical behavior, which is sort of what one would be describing with non-relativistic quantum mechanics. And the idea is that this fast timescale is unresolved in quantum mechanics, and the scale is that of the Compton frequency. This is basically proposed by de Broglie as the sort of root of vibration in quantum mechanics. So next slide, please. So the other, the more recent analog we have is a similar sort of system to that in the quantum corral. So here we have the so-called Friedel oscillations. These happen when you have a metal surface and you have a sea of electrons, and you put an impurity in it. Then as the electrons scatter off this impurity, you get this wave-like structure. And this is simply modeled with a Schrodinger equation with the localized scattering potential. But again, there's no notion of how the electrons are actually moving. So if we look at the next slide, we'll try and do the same with our system. So now we have a drop moving towards a well, which acts to attract them along an Archimedean spiral. And so they come in, and as they cross the well, there actually speed oscillations generated, and these oscillations have the wavelength of the guiding wave, that is to say the Faraday wavelength, which in all of the analogs plays the role of the de Broglie wavelength. And so again, in the fullness of time, you see this these concentric rings about the center of the well. So next slide. Oh, we didn't see, yeah. So there we see the pattern, and that gives rise to a PDF, which for all the world looks like Friedel oscillations. Okay, so again, we can conclude that Friedel oscillations are not inconsistent with the notion of particle trajectories. Next slide.
Hey, John, did I mess up an animation here just before we...
That's okay. That's okay. Next. Oh, okay. So you're right. So these are just two of a growing grocery list of hydrodynamic quantum analogs, so developed in Paris and in our group, and in Belgium, where there's another very active group, and there are others now in Australia. But so so the idea is to develop these analogs and then rationalize the emergent quantum-like statistics and get some insight into how quantum dynamics might be working. So we've seen, in particular, again, the key feature is the resonance condition between particle and wave, the monochromatic wave field accompanying the particle. And the limitations are the viscous damping of the pilot wave. It's the pilot wave, after all, that gives rise to the quantum-like features. In particular, in the case of orbits, it gives rise to orbital quantization. And all of the quantum features emerge in this so-called high memory limit, where the waves are weakly damped. And we've also seen that the drop inertia may dominate the pilot wave force, so spin states, which might otherwise be stable, are unstable in the lab, but we can let our imagination run a little bit. Next slide. And so as we look at all of these HQAs, as we call them, hydrodynamic quantum analogs, we look for the sort of underlying mechanism responsible for the emergence of quantum-like behavior. So basically, again, all of them depend on this resonance condition between the drop and the wave, and the particle basically exploring its non-local self-potential. So the three paradigms in orbital pilot wave dynamics: particle moves on a circle, it generates a quantized wave field, and they're basically it creates a wave field, and there are certain quantized orbits which are stable, and when the system becomes unstable, it flips periodically between them. So you basically, chaotic pilot wave dynamics gives rise to quantum-like statistics in these orbital pilot wave systems. Then we saw in the Friedel oscillation case, we saw how inline oscillations can give rise to a statistical signature with the Faraday wavelength. And we've also seen systems in which you get this structured random walk with a step length basically prescribed by the pilot wave length. And so you get a diffusive behavior, which is reminiscent of that suggested by Nelson in his stochastic mechanics. Next slide. Okay, and so this we know this is simply hydrodynamics. This is a millimetric drop walking on a vibrating bath, and we certainly don't expect to capture all features of quantum mechanics, and we know that we can't. We're limited again by fluid viscosity, and occasionally particle inertia, but we can explore a generalized pilot wave framework. So this is basically suggests a new class of dynamical systems, which is broader than the hydrodynamic case, but encompasses it. And so we'll look now at this dynamical system. What can we do if we retain the key features of the Walker system? That is to say, memory, which gives rise to non-locality, resonance, and this quasi-monochromatic wave field, and we go beyond the range of the hydrodynamic system, and this will also allow us to connect to quantum pilot wave theories, in particular that of de Broglie. Next slide. Okay, so this is the generalized pilot wave framework. So if we just take our trajectory equation, so we have the inertial term on the left, we have a drag term, and then we have this wave forcing term, and that's, of course, the interesting one because that has the memory in it. Note the integral backwards in time. we have three terms, so we can assess characterize the relative magnitudes of these three terms with two dimensionless groups. The first one on the left prescribes how close we are to the Faraday threshold, so how long-lived the waves are going to be. And the term on the right contains all the fluid parameters, and it's basically saying how important inertia is in the system. Okay, and so it turns out that the term on the right is very tightly bound in the experiment. So it sort of varies from 0.8 to 1.6. And so it represents a limitation to the sort of list of analogs one can hope to get in the lab. So, but we can say, well, what happens if kappa naught is 0 or kappa naught is 10 to the 16? Then perhaps we can capture more quantum-like features. So in particular, so when are hydrodynamic spin states stable, and when is the system unstable to inline oscillations? So next slide. So we can, again, now we've sort of generalized our pilot wave dynamics and can start looking for other quantum-like features. So it turns out that in a certain parameter regime where kappa naught is small, one can stabilize spin states. So a spin state I'm calling a drop walking around in a circle trapped in its own wave field. And this is just unstable in the lab. You can sort of see vestiges of them, but they're just unstable. Next slide. And if you look more generally at the free particle in this two-dimensional generalized pilot wave framework, you have not only spin states, you have wobbling spin states, these quasi-periodic orbital states. And so there's just a two-parameter family of dynamical systems. And so and then you can see that you get these inline oscillations in a great majority of the parameter space. And then you have the sort of random walk in others, where again, it's a structured random walk of the sort described by Nelson. And so you really have this very rich behavior for this set of dynamical systems, which promises the possibility of, for example, spin states and other things, which we know will give rise to quantum-like statistics. Next slide. Okay, so but that's using one particular waveform. So that's using the waveform that's relevant in the hydrodynamic case. You can imagine other waveforms. So that represents a direction for further generalization of this pilot wave dynamics. And also extending to 3D should allow us to explore new analogs. What I'm super excited about is that this has been connecting. So it connects both to the hydrodynamic system, and it also connects to de Broglie's mechanics, as we'll see. So this is informed a recent extension of de Broglie's mechanics, HQFT, which I'll describe in a moment. Next slide. Okay, so let's go over de Broglie's mechanics. So what he said was every particle has an associated vibration, and this frequency of vibration is prescribed by the Einstein-de Broglie relation. So relativity tells us E equals mc squared. Quantum mechanics tells us E equals h bar omega. That defines this Compton frequency. And de Broglie said that that frequency, there's an exchange between rest mass energy and field energy. Next slide. And so this is basically playing the role of the bouncing in our system. Okay, so his theory was called the double wave solution because he imagined this resonant interaction between a particle and the wave generating a real pilot wave, and then that would give rise to a statistical form, which was described by Schrodinger's equation, by the standard formulation of quantum mechanics. Okay, so he said that the wave, this pilot wave, the real wave, is a solution of the Klein-Gordon equation, and he said that the particle follows a line of a constant wave amplitude or constant phase. And this gives you basically P equals h bar k, provided you have a monochromatic wave, okay? And he also stressed this harmony of phases, so the resonance condition between the particle and the wave. So this is a very nice idea, which again provided some of the, a cornerstone of some of the cornerstones of quantum mechanics, in particular P equals h bar k and the Einstein-de Broglie relation, but he didn't say how the waves are generated. So he couldn't resolve the interaction between the particle and the wave. So this is what we're attempting to do, again, informed by the hydrodynamic system. Next slide. So the nice thing to bear in mind is this really is a macroscopic realization. This hydrodynamic system is a macroscopic realization of what de Broglie imagined. So he had this fast time scale on the Compton scale, responsible for wave generation. Then the P equals h bar k is basically the strobe dynamics you get from resulting from the particle interacting with its wave. And then you have this emergence of the long-term statistical behavior. But he didn't specify what the field was. So go next slide. So there's several possibilities. One is the the Higgs field, he said that it was a solution of the Klein-Gordon equation, in which case it would be the Higgs field. The approach taken by De La Peña and Cheto is that the background field is the electromagnetic quantum vacuum. The nice thing about the electromagnetic quantum vacuum is it has a particular spectral form, in particular the energy in a mode with frequency omega is h bar omega over 2. So this is the way that you get h bar into a classical theory. Next slide. And so you can then put the de Broglie's mechanics and its extension in SED on the same page as Walker's, and you have this nice map between the two. In particular, this Zitterbewegung, or high frequency oscillation, the competent frequency, its role is being played by bouncing, and surface tension is effectively playing the role of h bar in the hydrodynamic system, and the Faraday wavelength that of the de Broglie wavelength. Next slide. Okay, and so this hydrodynamic quantum field theory is basically trying to extend de Broglie's mechanics in a way that was suggested by Holland. So actually putting in a source term in the Klein-Gordon equation. So this is work done by Yuval Dagan, who I hope has finished his teaching, is with us now. So, but basically we consider a particle as a localized forcing in the Klein-Gordon equation, and then we consider a relativistic guidance equation. We actually consider the zero particle inertia limit. So we're currently thinking about how to get particle inertia back in there. Of course, we would like it to be consistent with relativistic mechanics in the limit of zero waves, but we're working on that now. But this first attempt was simply looking at the zero particle inertia limit. And so we simply have a balance between drag and a wave force. Next slide. So when we do this, the particle, when there's basically a coupling constant and a critical value of the coupling constant, the particle will start moving just like the droplet does. So it basically vibrates in place, and then will start self-propelling, and it propels in such a way that P equals h bar k. Next slide. Sorry to invite the green frog into our and also, so if you look at, there are also online oscillations, and these oscillations have a frequency CK, and so this sort of provides a rationale for the relativistic dispersion relation. So there's an energy associated with the particle vibration, and then associated with its inline oscillations. Next slide. So, and so we've looked in the non-relativistic limit, the pilot wave actually converges to a plane wave with the de Broglie wavelength, which is very nice. In terms, I think we'll be able to get a nice version of slit diffraction if we use this HQFT. Next slide. And so again, in the low speed limit, non-relativistic limit, you have a plane wave. And when this, the guiding wavelength approaches the Compton wavelength in the relativistic limit, and so you then expect to get structure on the scale of the Compton wavelength, and this is these spin states would then correspond to analogs of the classical model of the electron, where you have a charge zipping around the Compton wavelength at the speed of light. Okay, and so. Next slide. So there are all sorts of nice connections between the hydrodynamic quantum analogs, the generalized pilot wave framework, and this hydrodynamic quantum field theory, which is of course encouraging. And so through LSI, we want to basically develop theoretical models of vacuum-based propulsion of particles. And so basically assess the viability of a vacuum-based HQFT as a rational quantum dynamic. So it's really fundamental issues about the vacuum. So can we really come up with a rational quantum mechanics, and can this inform the possibility of vacuum engineering? Okay, because I mean, when you think about it, the particle is, you have a vibrating particle interacting with the background, and it's self-propelling, right? So you see how vibration can lead to self-propulsion, okay? And so the approach will be both theoretical and numericals, modeling of these HQFT and the generalized pilot wave frameworks, all of which were inspired by the hydrodynamic system. And particular, as we go to 3D, There are new analogs that we can look at. We know that some of them work in 2D. So in particular, the simple harmonic oscillator, we have a very nice analog of that with a hydrodynamic system. And so is that going to work in 3D? We hope so. And we can now we can also look at motion in a Coulomb potential, in which case we can get a 3D analog of the hydrogen atom. Next slide. And so the team, so there's myself, so Adam Kay is being supported directly by the LSI. So he's a recent graduate from Oxford, who's joined my group, though is remote at the moment. And he's just getting started. And Matt Dury and Yuval Dagan have been the pioneers in the HQFT, and they will also be contributing, no doubt. And in terms of timeline, so Adam is just getting started. He's actually hiding currently from a fire which is raging near his home in California. So hopefully that will turn out okay. So we'll begin with basically ramping up the project. So looking at developing numerical and theoretical models of both a three-dimensional generalized pilot wave framework and a hydrodynamic quantum field theory. And we'll hope to wrap up next summer through writing. So sorry for running over.
Awesome. Thank you for the talk, John. I really appreciate it. And I figured at least one of you guys was going to get the green frog before the end of the presentation. I don't know if folks online could see that, but we talked ahead of time. I got this idea from Hal Fern. She used in one of her Zoom meetings, she used a big red alert sign to let the speakers know it was the end of their session. And so I added a little bit of an exclamation point in the form of a frog here. For the folks that may not have seen it, it goes from this to this. So that's when you heard John talk about the green frog, he wasn't having some kind of moment or something. He literally saw the green frog. So thanks everybody for your talks this morning in the morning session. Let me just start off by saying, wow, I'm really enjoying myself. This is a lot of fun to get this quality time with you guys to share some of your amazing ideas and thought processes. And when you review papers and proposals and so forth, that gives you a certain level of understanding of what somebody's proposing, but it sure does add a whole lot to it to get in your guys' voice and in your story what it is you're thinking about, what it is you're excited about, why you're pursuing it, why you're spending your time on it, right? Because these things are things where you're committing one of your most precious resources to, your time, to go pursue. And so it's neat to hear what it is about these ideas that excite you and how you think they can potentially be of value. So first and foremost, thank you guys for that. So now let's move into the Q&A portion. Let me unshare my screen. Okay. So for folks that are in the attendee list, there are two ways for you to provide us questions. We have a Q&A tab that you can provide, and then there is also in the chat panel. So Dylan and James, I think I've been asking you guys to monitor any of that. Let me pull my chat window out so I can see more of the text here. And I think there's we have a handful of folks that are over on the YouTube live stream. There is a chat window there. We'll try and monitor that for questions. So I think that's first and foremost. Dylan, is there anything in the process of you monitoring the?
Yeah. There's actually a question for Phil Lubin from Jeffrey Landis. And what's the current status of the experimentation with regards to the COVID-19? Phil, has it had an effect on your experiments which you've been doing?
Sorry, I had to unmute myself. Yeah, probably like many of you, we have had to work around the COVID restrictions. So we were actually out of our lab for approximately 90 days. And now we're back in about 50% of the time. We've learned the new reality of Zoom meetings. So my life is purgatory of multiple Zoom meetings per day, of which this is another one. So thank you, Sonny. And I have more.
Okay.
This is the fun one, though.
This is this is much more fun than my other music. Yeah, I mean, it's had an impact, although honestly, I thought it would have everything grind to a halt, but we learned to work effectively and distributed the work, and so we continued. But now we're back in lab.
Great. I think I might allow Jacob D. Rodriguez to talk. So Jacob, I've read your question. It looks good, and I'm going to try and allow you to talk now, Jacob D. Rodriguez. So if you want to speak your question.
Hi guys, I know you can't see me, but I'm a current freshman here at MIT. I'm actually taking Professor Bush's 1802A class, which is cool, and he was able to send me the link. And I guess like the biggest question, especially for you, hopefully we actually be able to talk about this in person, which would be fun. It's more like I did a lot of reading on it, and then since I followed Sonny's White's research after he sent me a lot of the stuff, I basically like want to know, there's a lot of like criticism towards like your explanation of using like the analogs to kind of just replicate a pilot wave theory. And I read like one article in Quanta in which like you guys tried to replicate the results from another research lab and you guys couldn't in terms of a double slit experiment. And I just kind of wondered, like, the research you guys are doing are really cool. So how did you guys bounce back from that? And how did that kind of affect your outlook moving forward in research?
Yeah, so this is a good question. So I know there's this scurrilous article in Quanta, but the history of it. So Couder did this really exciting experiment where they basically sent these walking drops towards slits, and they found a diffraction pattern. And then they did double slits, and they found a different diffraction pattern. And their work suggested that not only do you get a diffraction pattern, but the particle, as it passes through one slit, it feels the other slit. And this is, of course, that's an expression of non-locality, and that we have many such expressions of non-locality. Now, this is one of them. And so they had their experimental results. We went back, and so they did these experiments at a time where they weren't measuring either the drop size or the acceleration. Nevertheless, they had this pattern emerging, and it was slightly different from the quantum pattern, but that doesn't bother me. And so we went back and we did this, and of course, because they didn't report what corner of parameter space they were in, it was like a needle in a haystack finding the parameter regime that they were working in. But we explored all sorts of parameter regimes and sort of focus on one in which we got something quite similar to what they had. And so again, it's similar to what they had. It's different from quantum mechanics, but that doesn't bother me. We definitely showed that as a particle moves through, if there are two slits, as it moves through one slit, it feels the other slit. And this is by virtue of the fact that it's global pilot wave, so which is influenced by both slits. So it's approaching, it's basically carving out a local topography. And so that topography changes form if the other slit is open or closed. So that's the real mystery of the double slit, and that is captured by our system. So then Thomas Bohr did experiments. He couldn't reproduce the results that Couder had, but his experiments in his first run at it, his experiments weren't as well controlled. So we went back, we basically got things which were comparable to Couder's, but again, you can't compare unless you know what the parameter space is. And then, but now most recently, another group in Denmark repeated the experiments, and they did the most controlled ones to date. So we basically found that you had to put a lid on because any small wind in the lab will screw up your results. And so, but we got repeatable results. And they basically, so this new group went back, they did things with the lid, and they also had temperature control. It turns out temperature control is very important, but they basically got the same results as us and came to the same conclusions, all right? So the conclusion being, you get a diffraction pattern, which is slightly different from quantum mechanics, but who cares with how many, what the details of the diffraction pattern are, right? But they also found that you have an influence from the second slit. So in my view, it was a first expression of non-locality, and all of the experimental evidence suggests it, but it's just one in many. I mean, this is what you have to realize with the system. You are not going to get exactly the same things as quantum mechanics. Quantum particles are not silicon oil drops walking on a vibrating bath. There's something different. There's a different form of the wave field. The boundary conditions on the wave field are going to be different. But this non-locality is the key feature of both systems, and we can rationalize it with our physical picture.
Thank you, John. Appreciate it. Very good answer. Just real quick.
And sorry, if I just say one thing, that review, this one, if anyone wants to just send me an email and I'll send you the review, because this covers this. I beat that subject to death there, and then I'll send it to the author of Quanta. So.
Yeah, I did get a request for your lengthy paper. Somebody was wanting a copy of it, so you could send me a copy, and then anyone online, they've got my email, they can send it to me, and I'll distribute it that way. Of course, I think you can also reach John directly. You can find all kinds of his papers online. Let's see. Got a couple questions here in the chat window. Actually, before I jump to that, I did have a question for the two fusion talks that we had. I know in the last 12 months, the National Magnetic Lab at, I think it's in Tallahassee, Florida, they've conducted a couple of tests to break the record for magnetic field that was achievable with a superconductor, and they've been using, I think, this Reedco tape that's pretty common nowadays. And they were able to achieve very close to 50 Tesla magnetic field in a controlled laboratory setting. Yeah, that's a lot. And so I know that magnetically confined fusion is certainly seeing a resurgence of interest because of the capabilities that have been established with Reedco high temperature superconducting tape. It can achieve very, very high field levels, and this material is very, very robust. You can abuse it in an industrial sense, if you will, and it behaves very well. So I think it's opening some pathways for magnetic confined fusion. It might shrink reactors from what we see with ITER. But with that said, as a little bit of a preamble, is in your mind, is there having this very, very large magnetic field capability available to you, would that tweak anything you're thinking about in the two fusion concepts we heard today, this morning?
Ray, do you want to start?
Sure. So it's not so much that they are able to achieve such a high field level as that means that at larger scales you can achieve larger fields than you can. So I don't think necessarily a 50 Tesla field is something that we would necessarily utilize, but certainly it means that at a larger scale that might have because we would like to have a relatively large volume of fusion plasma, and so certainly that technology allows us to generate higher fields at larger scales with overall lower mass systems that can run continuously, not having to run in a pulse mode. So certainly that technology is, I think, a key technology for what we're trying to achieve. Jason?
Yeah, so my take on it is that it appears that the higher the fields that you can generate for a lot of the concepts, the smaller the device can be. That's not universally true, but certainly it helps tremendously to be able to increase the magnetic field pressure, which means you can increase the density and lower the reactor size for steady state concepts. And in the context of a propulsion system, one of the things that's making it very difficult to close vehicle designs for even a Mars mission is nozzle heating. And so everything that you can do to cut down the amount of heat that's dissipated in that nozzle is going to help towards, realizing a propulsion system, at least for fusion. And so I think it's very exciting. All the different tools and technologies that are emerging that I think are really going to make fusion a reality in the next couple of decades.
Thanks, Jason. Thanks, Ray. Yeah, and Ray, just real quick, acknowledge me. I wasn't trying to say 50 Tesla was available, but I know in terms of like the spark reactor, for example, they're looking at going up from 5 Tesla to 10 to 12 Tesla, and so that's allowed shrinking. That's like ITER is 5 Tesla, and Spark is looking for 10 to 12, and so that allows them to shrink the size a little bit. So, Dylan, have you caught any other questions that have come up that
Yeah, there was a question in the chat from Jose Rodell. Jose, if you like, you can talk, or I can read out your question.
Can you hear me?
Yes.
Okay, I understand Professor Bush said that the process is non-Markovian, therefore it has memory, it depends on history. So what is the simplest probability description for this process? Is it, can it be described as a martingale, as an Ito process, or as a long memory Hurst fractal process, or what is the simplest probability description for this memory dependent process?
So I'm not sure what is a martingale. I don't know I don't know the nomenclature. So
okay.
What would can you give me an example of a martingale process?
A martingale essentially has a memory where the autocorrelation, it depends on the autocorrelation is non-zero because of memory. And you know what the Hurst fractal process is, like Mandelbrot describes.
Yeah, no, I don't know this nomenclature. So I'm using it in the dynamical sense, the non-Markovian. I'm again in the dynamical sense rather than a statistical sense, simply saying that the instantaneous force acting on the particle depends on its history. So it is, I mean, how this is manifest, how this dynamical non-Markovian feature is manifest in the statistics is really something we're coming to grips with. So
essentially you're using an integral with that the memory is represented by an integral. So another question is the memory a fading memory, a short memory, or is it an infinite memory going all the way to the remote past?
So good question. So in the case of the hydrodynamic case, the memory is limited because it's basically limited by viscous damping, and all of the quantum-like features emerge in the long memory limit. That is to say, the weak wave damping limit. So that's really when you get the quantum-like features. So when we've gone to HQFT and when we go to the generalized pilot wave framework, we want to look at that weak wave damping long memory limit, and that's really when the party starts. And that's certainly, for example, in the corral. Then you have a particle in that corral geometry. You in the zero wave damping limit, you basically have the thing exploring the wave mode of the cavity, right? And so then it's exploring this non-local potential, which looks very much like the Bohmian potential, like the quantum potential in Bohmian mechanics.
Thank you, John. I appreciate it. I think I'm going to switch to a different question. I was looking in the chat window and I accidentally moved a question from the open to the answered. I have no idea how I did that. Derek Coldeneau has a question for Jason Cassibry and Ray Sedwick. He says here, in terms of confinement of fusion-capable plasmas, have you encountered any instabilities which may destroy coherence of either the Z-pinch or the magnetic mirror? And then he has another question. The stabilization of flute instabilities was mentioned, but do you foresee other limiting effects for long-term continuous fusion applications? So
I'll start on this one. Instabilities in fusion, I'm not sure I understand the question at all. I'm just kidding. Yeah, no, instabilities are one of the major difficulties in fusion. And it's a great question. I'll just speak on Z-pinch in particular. It is prone to the M equals 0 and M equal 1 instabilities. These are instabilities have to do with the pressure and magnetic field pressure balance. And there are a number of ways to mitigate that instability. So for example, you have Uri Schumlock's ZAP concept, in which he has a shear stabilization, in which he has an axial velocity with a radial shear in that axial velocity profile, which strips off some of the instabilities. You can also stratify the density in the radial direction, and that can offset that instability. And the way that we are going about it is relying on the fact that empirically you can observe that the Z-pinches tend to go unstable right when current reaches its peak. And the best way to kind of understand that one is to look at it from the magnetic vector potential equation, in which it's basically posed as a second order time derivative balanced against two terms. One of them is current density, and the other one is a second order derivative in the spatial gradient of the magnetic vector potential. And as long as it's being dominated by current, you don't have that other term. But once you start to relax and the current reaches a level value, that second order derivative kind of catches up, and that's when things become in mechanical equilibrium, and that's when your instabilities tend to occur. And so what we're trying to do is to reach a parameter space just before the pulse reaches that peak. But as with all fusion concepts, fusion has a way of humiliating everybody that's enthusiastic. So we're just going to approach this and look at the data and try to react based on what that data tells us.
We need to have a support group, right?
Hello, I'm Jason. I'm a fusion researcher.
That's great. Sorry, Ray.
So a little less detail than what Jason provided, but so the MCX experiment did demonstrate that this shear velocity flow does seem to over multiple MHD timescales suppress possible instabilities that could arise. So we don't necessarily expect any sort of large disruptive instability, but some of the things that we do still have to investigate are, what residual transport phenomenon might there be in excess of sort of classical transport. So there's still the question of the transport of the plasma radially outward, and what sort of time scales we would have for that, sort of longer than sort of the instability time scale. So at least at the moment, we don't anticipate any major disruptive instabilities, but as Jason points out, confined plasmas have a tendency to embarrass us. So as we investigate further, it's quite possible that something will come up that we're not expecting.
Thank you, Ray. Real quick, I have a question for Phil. So Phil, you had in one of your charts, you talked about a LEO wafer sat concept. Could you maybe speak just a little bit in your mind? I know you and I have talked a little bit about the surface of the moon type of applications, but what are some of the sizing parameters associated with a LEO wafer sat experiment? And you know me, I'm always going to ask you, what's the minimal amount, how small can you make the laser? How small can you make the LEO wafer sat? And can it be in orbit, beaming from a static source to the wafer sat, or is it better to be on the ground? There you go.
Yeah, so one answer is that don't limit yourself to any specific size of spacecraft, but say you have an asset in LEO and you want to transfer power to the asset. There's certainly a lot of assets in LEO where you'd like to keep them up longer. So transferring power to an ion engine to counteract the atmospheric drag would be highly useful for many people, particularly within the surveillance community. The size of laser aperture you need is only about 1 meter to get to a LEO target. You can project 1,000 kilometers and have a 2-meter spot in terms of the area disk from a 1 meter aperture on the Earth or in space. It's vastly simpler to start on the Earth. So the idea of transferring power from ground to LEO, I think, is not a crazy idea at all. It does not require a large aperture. In terms of the power level, the power and aperture are relatively agnostic here. So you could transmit, a kilowatt to LEO this way, or you could transfer a megawatt. It doesn't really make all that much difference. Obviously, there's a cost difference between those two. But in the models that we ran, just transferring even a few hundred watts to LEO to run an ion engine makes a significant difference. And those are things which are well within our capability of doing. And they also provide a step along the ladder of getting to these, higher functionality missions. But it's a completely scalable technology. And in that sense, I think it's very different. If you wanted to produce a bottle rocket to get into orbit, that doesn't work very well. It doesn't scale properly. If you want to use a directed energy system to get from here to LEO, to the moon, to wherever, that does scale in a very different way, and it scales very, very nicely. Does that help?
Yeah, that does. I just want to, if I could embellish my question, what if you had a power beaming source of a kilowatt or 2 kilowatts on ISS going to a CubeSat? Is that something that would be even remotely of interest in terms of performance?
Yeah, definitely. And we had a lot of discussions about 5 years ago with people that were working on ISS. What would you think if we put a multi-kilowatt laser on the ISS? And the answer was always, well, you'd have to run that through so many review committees. It probably would be much more complex. What happens if you turn it around and you burn a hole through the ISS?
Well, we have pretty powerful antennas on the ISS, and they have a lot of safety things that preclude that. So it's
yeah, and I would
handle that. So.
I would love to work with one of your partners that has access to the ISS in terms of doing a test like this. Absolutely.
Okay, so I think that was a corollary, is that there might potentially be value in exploring that discussion. Okay, all right, that's what I want.
Absolutely. Yeah.
All right, Dylan, back to you. What else you got from?
There's a couple of questions there. One interesting one. So this is for Jose from Hal Fern. Do you think we could use a forced kg equation for a scalar field in modified G-OR to explain Jim Mach effect motion? Jim's Mach effect motion. Does that make sense?
Oh, I think that was a question between Hal and Jose Rodel. Okay. Yeah, I think she's just exploring the implications of the forced Klein-Gordon equation for a scalar field, applying it to general relativity. Yeah, this is just between them. It is an interesting question, but not for our panelists. Let's see.
There's 2 more questions there in the Q&A.
Yeah, well, one thing on some of the questions, I'll make sure for folks that are asking questions, try and keep the questions related to the talk material that we went through. I want to just keep it focused on their work. Let's see. I do have one question for John Bush. In the process of me talking about Venn diagrams and physics, I think we can all agree quantum mechanics gave us a really cool toy that we really like to use. In your exploration of your hydrodynamic quantum field theory, you're thinking a little bit about some unique applications from our perspective, right? Some power and propulsion things. But are there some other things that have popped into your mind in the process of exploring the physics that you're working with that, hey, this might lead to this effect, which could lead to some neat technology outside of?
Yeah, I mean, it's certainly not, it's not technologically driven. It's really, the goal is to understand the fundamentals, and having a physical framework for understanding a subject is invariably going to lead to better understanding and technological advance. And their history is full of such developments. And so I really think going for trying to understand the most basic questions. I mean, I remember I read an interview with it was with Einstein. They were talking about, how do you feel about entanglement? Are we going to understand entanglement? He said, I just want to understand what the electron is. And I'm sort of the same camp. You know, if you understand basics, then these are fundamental building blocks from which you can build all sorts of things. And so there is something to be said for understanding things at the most fundamental level. And this gives a physical picture, and we're sort of exploring its range. And it has limitations, but then we can get around those limitations by exploring a broader class of dynamical systems. And I think, I do think that there is value in fundamental research, regardless of direct applications.
Okay, cool. Thank you, John. I got to go ahead and push pause, if you will, on the morning session. We have a break scheduled. We've had a lot of good questions, a lot of good material. So we're gonna have to cut the break just a little short. It is 10:26 right now. So if we could take a small break, if anyone needs to go get another cup of coffee or a drink of water or whatever you need to do, we will convene back at 10:40 Central Daylight Time. So that's in just 13 minutes from now, if you will. So I'm going to keep the loops up. The YouTube Live will stay up. We're just going to take a pause and step away. So same bat time, same bat channel. Sonny's back in just a couple minutes. We'll get started here. I got my coffee. I hope everybody else got some more deuterium in their fuel tank. Okay, just a couple sentences before we get started here again. For folks that are in the attendee section, if you have questions, just type them in under the Q&A window that's in the bottom of your Zoom window. If you kind of hover your mouse, it'll bring up several different options, and one has like a little Q&A button. It looks like a cartoon characters talking balloon, if you will. You can also put it in the chat if that's easier for you. We will try and monitor both of those. Certainly, we got more questions than we could answer during our first 30-minute session. The same may be true for the second 30-minute session. We'll do the best we can to try and catch as much of them as we can. We may go just a minute or two long in our afternoon Q&A session. Keep the questions focused on the technical materials that we're covering. If you ask questions that are outside the scope of what we're talking about, while those are interesting, those are not the ones that we're going to be able to focus on because of time limitations. So again, just want to say some words of appreciation to all the folks that are on the panel here with me. Our 9 performer teams, thank you everybody for giving us some of your time, pulling together some presentations. I am so enjoying myself. I'm definitely geeking out big time, getting a chance to listen to all the great math and physics talks and so forth. So this is right up my alley, right? So definitely enjoying it. I hope everybody else online is enjoying it. If on the attendee panel, if something comes up during the Q&A that you feel you can't type in to the window, like it might be too long of a question, you can raise your hand and Dylan and James will be watching for that and potentially promote you into the panelists so you can share your question verbally. Maybe we can do some Q&A. So with that, let me go ahead and just get started. Let me be as much of a schedule hawk as I can. So first up, we have for our midday session here, we have Richard Norte joining us from Delft University of Technology. It's a presentation on some relativistic sail technology. It's a much longer title than that, but I'm trying to keep it quick and short. So Richard, let me pull up your charts. And make sure you are off of mute.
Yep, I'm off mute.
Okay, I have your charts. You have the microphone, sir. Thank you.
I don't see your
stand by.
Sorry, I actually don't see your slides or my slides. There they are.
There. Yeah, my bad. It was a problem with the organic interface again. Sorry.
Oh, that's fine. That's fine. Thank you. All right. So thanks everyone, and I especially want to thank LSI for inviting us to this really nice event, and also for the support for this project. So this is a project collaboration between me and Miguel Bessa, and we're both at the Delft University of Technology in the Netherlands. And what I'm going to be talking about today a little bit is origami of photonic crystals, which we'll be designing with machine learning algorithms. So I guess we can go to the next slide. Okay, so I actually really like this infographic because I think it kind of nicely shows this kind of innate drive that we have, and especially I would say a lot of us at this event have for exploration. Humans have really tried to find a way to get off of our little rock. So you can see here we've got about 72 missions to the moon, about 38 missions to Mars. So we've really tried to expand out quite a bit. And if we go to the next slide, you'll see that if we go out to the outer solar system, you start to see, well, the density of missions starts to get smaller, but yet we still try to manage to get out there. A lot of these you'll see here are actually Voyager 1, Voyager 2, Pioneer. So a lot of these are, for instance, using these outer planets as gravitational slingshots. But if we go out even further and we kind of look on the interstellar scale on the next slide, if you look at, for instance, Voyager, which is essentially the furthest traversing man-made object we've really ever made, it's been going on for about 47 years, and if you look at how long it would take something like Voyager to get to Alpha Centauri, you're really talking on the order of 10,000 years. So this is just more of an overview of kind of the challenges, but I think a lot of us are very familiar with this. So if we go to the next slide. So one of the proposals that's been gotten a lot of attention recently is this idea of using light sails with laser radiation pressure to essentially make a sail that is sub-gram or gram scale, and propelling this sail with a chip to about a fifth of the speed of light. So this is something that was also outlined in this roadmap by Phil Lubin, and so the idea here is to really reduce these mission times from something on the order of 10,000 years to 20 years. So we can go to the next slide. Okay, so this is just the general kind of explanation of what the concept is, but obviously it's going to be much more complex when it's actually really realized one day. But here's kind of a general idea. And so the idea here is that you would have your probe would no longer be a manned, we're not talking about manned mission anymore, but we're trying to see how light can we make a probe that has cameras, radio, antenna, microcontrollers, energy system, communication systems, all of this on a chip. So here we're thinking about something on the order of, millimeter size with sub-millimeter thickness. And the mass, I actually made a mistake here. So there should be a milligrams in front of that mass. So 220, milligrams, let's say. So this is really a sub-gram kind of probe. If we click to the next slide. And so really the idea here is that what we want to do is grab some kind of chip like this and attach it to really large sails. Really large being something on the order of 4 by 4 meters. That should be under a gram. The idea is to push this light sail with about 100 gigawatts of Earth-based laser radiation. And if you look at what is that critical? So if you really want to get this whole 4 by 4 sail down to a gram, then you're talking about a critical aerial density of about 0.0625 grams per meter squared. So this picture here is obviously not to scale at all. If you go to the next slide. So really what it's really hard to even think about the aspect ratios that are really involved in this kind of application, because you're talking about something that's 4 by 4 meters that we have to get down to half the weight of a penny. So this is really a new type of nanotechnology. So we can go to the next slide. And I think this is really the kind of important part of this is that if you look at the technology that's going to be required over the next decades to get the chip-based probe to get smaller and smaller, making the radios smaller, the gyroscope smaller, the communication system smaller, the camera smaller, all of this really goes in line with conventional miniaturization, right? So we're always trying to make things smaller and XYZ, get it smaller, and that's really a kind of a conventional way of thinking about nanotechnology. And kind of what sets the light sails aside as a really special component in terms of its difficulty is that you're really talking about nanotechnology in which you want 2 of the directions to be in the meter scale, and you want 1 of these directions to be on the nanoscale. And that's really a very different direction than most nanotechnology people are used to thinking about. So I think we can go on to the next slide. Yeah. So if we think about if we think about what can actually give you this kind of sub-gram or gram scale masses when you make something 4 by 4 meters that has high reflectivity, low absorption, there's really there's only really a few materials that can do this. And the one that we've been developing quite a bit at the TU Delft has been photonic crystal membranes. So the idea here is essentially you grab a dielectric film, something on the order of 50 nanometers thin, and you essentially nanopattern holes into it to make it an ultra reflective mirror. And the reason I'm kind of dialing it on 50 nanometers is because 50 nanometers is essentially a 50 nanometer silicon nitride film, which is what we use, would be what you would need to get to this gram scale if you were to expand it out to 4 meters. So it's really now already kind of at the minimal thickness, and with these kind of photonic crystals, we can get something on the order of about 90% reflectivity. So it's actually quite good for its thickness, and that's considering that this thing is only 50 nanometers thin, and it's really reflecting light that's about 1.5 microns in wavelength. So that's quite interesting in that sense. So if you go to the next slide, you can see what these look like on a closer scale. So at the bottom right, what you see is a scanning electron microscope picture of what these photonic crystals look like. And the way they work is here on the left, you'll see the blue dashed line. That's what the reflectivity would be of one of these silicon nitride membranes without any holes in it. If I just shot some 1064 light at it, it would just be essentially on the order of about 30% reflective. And what you do is when you punch these holes into this photonic crystal into this dielectric film, you can actually make it highly reflective. Really, if you make it, for instance, a little bit thicker, say go to 200 nanometers, you can really start to make it something on the order of 99.6% reflective. And here in this blue square, you see a simulation of what it looks like. So essentially what happens is you have this kind of trapped mode that lives in the membrane. And this mode essentially destructively interferes with things with the light field on one side and constructively interferes with light on the other side. So you essentially make a reflector. So this is kind of just to give you a sense of generally how a photonic crystal works, how you can get such high reflectivities from such a thin membrane. And this is pretty well-known way of making photonic crystals. So this is this is not, I would say, new technology in that sense. I think this has been done now for at least a good 15 years. So if we go to the next slide. Can we go to the next slide? Oh, sorry. Sorry, go back. You can go back. I forgot. And so one thing that is a big issue for a lot of these interstellar applications is what you're doing is you're propelling this thing to super fast velocities, right? And so what's going to happen is that there's going to be some Doppler shifting that occurs when this happens. And so right now, the way that the photonic crystals are made, you can see that they're reflective, but they're only reflective at a very specific wavelength, which we can tune to whichever wavelength we want. We can tune it to be reflective at whatever wavelength we design, just based on the size of the holes and the pitch of the holes. So one idea is, can we make a photonic crystal mirror, for instance, that could have a wider band, a wider bandwidth to account for this Doppler shifting? Can we go to the next slide? And here it's just a little bit of a illustration to give you a sense of why is this different, for instance, from solar sails. Solar sails have actually accomplished really impressive aspect ratio. So now they're making things on the order of 14 meters by 14 meters. And you can see there, for instance, so I'm talking about the Icaros solar sail, and it's really a polyamide sail that's about 7 microns thick, and it's made with a reflective metal layer on top of it to make it reflective. And then right on top, what you'll see is a scale drawing of what these photonic crystals look like in comparison. And so you start to really understand why it's so difficult to, for instance, make a silicon nitride photonic crystal membrane, for instance, at these really large scales, because not only is it much thinner, but it's also punched with nano holes at every micron, for instance. So this is really a quite delicate structure in some ways. It just depends on how you treat it. And one thing that I think is quite interesting that makes it promising for these kind of applications is we have shown at Delft that we can make these things on the centimeter scale, which is not something that people are really doing anywhere else right now. The other thing is that we were able to show that actually by making them larger and having a bigger beam that could kind of overlap with more holes, as opposed to kind of conventional photonic crystals, which are usually on the micron size, hundreds of micron size. By making it larger, we could actually overlap our beam with many more holes. And it meant that actually we could get a higher reflectivity from these larger sails than you could from a smaller test scale test size. And the other thing that we've shown is actually, if you go to the next slide. So these are actually pictures from actually my PhD thesis, and it was really on a completely different subject. So this is really about trapping for quantum experiments. But the idea here was that we were using trapping beams, which had a power density that's about twice the amount that's being suggested for Starshot. And you can see that that's more or less the limit at which these things start to pop from thermal fracturing. And these are done also in high vacuum, so it's very similar to the conditions that light sails will see in real life. So I think that's already very promising as a material that you can really put high powered lasers onto it, and have it still work properly. I mean, and it's not so surprising either. I mean, silicon nitride is not a new material. This is a material that's been around since CMOS processing was really around. It's usually used as an insulating layer. And I mean, it's also actually used to coat the nozzles of the shuttles. So this is really, this material is quite good in terms of its thermal properties. If you go to the next slide. And this is just to show how big we can make them in Delft right now. So this is me holding up one of the photonic crystals that I just fabricated in the clean room. And just to give you an idea, I don't have a cursor there, but if you see that there's these two little arrows pointing there, it's pointing towards a little dot, which if you can squint your eyes, there is a little dot there that it's pointing to. And that little dot is actually the biggest photonic crystals that people had been able to make before we kind of came up with our methods for making these. So now you can see that we've really blown up the size of these photonic crystals to by about 16,000 times. And that big square you see in the middle, that's really a suspended film full of holes, and that we've been able to show can reflect higher than 99%. So I think I will say that when the first announcements about Starshot came out, and they were talking about, for instance, these 4x4 meter sails, I really thought, wow, that's I don't know how that's possible, because what I was used to was making the things on the where the arrows are, and I think now after a few years of tinkering, I'm really quite optimistic that these kind of technologies could be possible if we really just work at it. So I think I found it quite promising over the last few years. Next slide. So now the idea is, okay, we've got these kind of conventional hole-based photonic crystals, and can we do more with this thin film? We have this thin film, and we have this problem where we've now made it as thin as possible. Can we get any more out of this, out of these kind of photonic crystals? Because right now we just have an ability to push on them, just kind of generally push on them with light fields. And the idea is, where can we go with this? So can we go to the next slide, please? And so the idea that Miguel and I have been thinking about is origami photonic crystals. So the idea here being that one of the things that makes these membranes actually so flat. So when you looked at that picture of a wafer, you saw that it's actually quite flat and there's not really any wrinkles on it. And that's because the membranes that we use are really under high tension, high stress, and that's just the way that they're deposited. And so now the idea is to use that stress in the films to actually make, instead of just having holes, making patterns inside of the holes that can essentially pop up like an origami, like a pop-up origami. And that's by using the intrinsic stress that's already in the films when we make them. So there's no additional kind of fabrication that needs to go into it. It's really a design problem. And so here what you can see is there's a side view of a regular photonic crystal. And then below it, there's a side view of what we imagine would be this kind of origami photonic crystal. And what you find is that even from a 50 nanometer film, we can essentially make it thicker without actually adding, more layers in the deposition. So we can essentially effectively make this membrane thicker and in a way almost make it more reflective and possibly increase its bandwidth without having to actually increase the film. And next. And so here the idea is also that not only can you get a more reflective film with more bandwidth, but maybe we can start to think about the idea of having chiral photonic crystals, things that really react to circularly polarized light. So this kind of is in line with some of the proposals that have been coming out of the Atwater lab, where they're thinking about torque-based stability of these membranes, for instance. And then one idea is also can we actually put some twist into these light sails? And I think that gives you another capability that's really not there with just hole-based photonic crystals. And the other idea is that maybe we can just increase the bandwidth of these things and actually get them to do this in a nice way for interstellar travel. So can we go to the next slide? And so these ideas really didn't come out from a vacuum. I mean, they really were inspired by Miguel's work. So he's done this really impressive work where he's essentially designed these monolithic metamaterial unit cells, which if you can go on to click one more time, which make these super compressible metamaterials and which has no hinges at all. So it's really just based on how these things bend, and he can get them to essentially twist and compress. So now the idea is to turn that idea, and the way that he's designed these is he's designed these using data-driven machine learning algorithms. And here what you're seeing are these are really micron-sized structures. So these are not big structures. This is actually quite small. And what we're looking at is going even smaller towards the nanoscale. But the idea for us is not to make something that's super compressible, but really actually doing the inverse of this and saying, well, we now have something flat. How can we get it to essentially pop up like a pop-up book? So we can go to the next slide. Okay, great. So for us, one of the main things here is we know we can make them large scale, but the idea is, can we add some functionality to it? Can we do something that's not possible with conventional photonic crystals? So for us, one of the main drives here is the idea is that to make a lot of small scale designs and use the data-driven machine learning algorithms to essentially, in conjunction with our testing setup, to essentially feed experimental data into the machine learning algorithm and essentially improve how we make these photonic crystals. How can we make them broader band? How can we make them pop up more? How can we make them more reflective? How can we make them more reactive to circularly polarized light? And so this is going to involve really making a lot of small scale devices, really, really small scale devices, and trying to make as many of them as possible so that we can just test through them very quickly. So that's going to involve not only the machine learning, but also making a laser-based characterization setup where we can really quickly feed through these designs. So right now our plan is really to first start with circularly polarized origami photonic crystals, just have some very simple designs to start with, and then really start to feed these into the machine learning algorithm to make them, for instance, more broadband. And so we're hoping that by the year's end, we should be able to have some really promising designs that could be used to get, for instance, larger light sails or larger membranes off the ground. So I think that this actually has a lot of nice potential with for instance, with other projects that people are working on, for instance, at Starshot. So I think that there's a lot of nice connections here with all our partners. Can we go to the next slide? And just to give a little bit of a snippet of kind of the capabilities that we have at the TU Delft. So one of the things we have are, we do have some optics laboratories for characterization. So this is where we're going to build these fast feed through setups. We have one of the largest clean room facilities in Europe at the moment. It's really super impressive facilities. And this is actually where we've already done a lot of the development of these photonic crystals. And the other thing that we have is well, actually Miguel Besa is actually heading a new institute called the Machine Intelligence Advances for Materials. And here what's going on is I guess the idea here is to really try to make an interface between machine learning scientists and material scientists to really come up with new materials. So it's really exciting what Miguel is starting here. And so here the idea is again really fast, small scale, fast testing, fast feedback experiments that can really feed into this machine learning. If we go to the next slide, yeah. And yeah, so I want to thank Miguel Besa, who's been essential in getting these ideas flowing and having these things, these really nice ideas. Simon Groblocker has also been collaborating with me on the larger sails. Peter Stanikin has also been collaborating with me on a lot of the optics. And then also thanks to my whole lab and yeah, thanks to Limitless and also everyone else for their attention.
Thank you. Appreciate it, Richard. I don't know if you noticed, but you got the frog.
Oh, I didn't see you. Sorry about that. Yeah.
That's okay. No worries, man. No worries. I figured you were getting close to the end there. All right. Yeah. So just push on forward. Thank you, Richard. Great talk. Thoroughly enjoyed hearing that. Next up, we have another fusion talk coming up. We actually have two back to back. Let me switch gears here and we'll get the next speaker. Kelvin Long will be giving us a talk. And you want your PowerPoint. All righty. Kelvin.
Okay. You hear me?
Thank you, sir. Yes, sir.
Okay. So first of all, lovely to see everybody. Thank you for Limitless Space Institute for organising this meeting and also the Breakthrough Initiatives for their support of this meeting. Really wonderful hearing the talks this morning. So I'm representing the Interstellar Research Centre, which is based in the UK. And I've been working with Limitless for a little while, but I'm very glad to be a part of this this group to move this kind of projects forward towards going incredibly fast, which is what we're all really focused on. So I'm sure you've all heard of Daedalus. I'm sure I mentioned this starship in every presentation I ever give, which for people who listen to my talks must find it a bit tedious. But I think it's one of the best kind of early designs of a starship that was ever undertaken. The reason it's important is because it was rigorously done by physicists and engineers. It wasn't just some people sitting down running some back of the envelope calculations. They published 23 papers looking at all of the systems from the propulsion to the power, the communications. It's really a good study and I recommend it to anybody. I won't go into all of the systems today because this is really a propulsion focused talk. But what I will say is it's a deuterium helium-3 system. It's two-stage, as you can see from the graphic. Sorry, next slide. Sorry, Sunny, I should have said next slide. I'm duplicating the slides on my other screen. I did my slide, but not yours. So yes, you can see some of the original drawings here from the actual report. So it's a two-stage system, and you know, beautiful graphic here by Adrian Mann. And if we go to the next slide, you'll see some of the actual numbers. There's a few graphics here just to keep you interested. So you can see it's got 46,000 tons of propellant for the first stage, and 4,000 for the second stage. So it's a flyby only. So it go to Barnard star in around 50 years. And thrust is sort of up there at the meganewton level. And you can see right at the bottom, something they didn't actually calculate in the reports, but I've calculated myself, the Q values, 66 and 33 for these two stages. Now the pellets for this system, the capsule pellets, were 1 centimeter and 2 centimeter in diameter. So this is an ICF based system. So what it has is these huge electron guns that go around the nozzle, and they impinge on the target as it's dropped into the target chamber. And this happens 250 times a second. So there's a lot of heat being generated in that plasma, which obviously somebody earlier was talking about nozzle heating issues. This is certainly an issue for this system in terms of fatigue on the structure. So I started a lot of my work on looking at Daedalus, and I like to solve problems in Fortran. I love Fortran for some reason. So I coded up Fortran to start with to model Daedalus and start to try to reproduce some of those numbers. What I realized is looking at the literature is that there's a lot of other studies out there which have been done, which perhaps lack a bit of rigor and also not on a consistent basis. And so I kind of want to turn that programming tool into more of a user design code. If we go to the next stage, the next slide. So I mentioned inertial confinement fusion. So I'm sure you're all aware of the Lawson criteria, which is this fusion triple product, number density times the confinement time times the plasma temperature. So for ICF, you're looking at something like 10 keV plasmas. So essentially what you're trying to do is impinge laser beams onto the outer shell of a capsule to rocket ablate the surface. Then the whole thing collapses inwards. And then you get this hot spot condition at the center, which hits your Lawson criteria. You get alpha particle energy deposition, and then you get thermonuclear burn wave, which ignites the whole thing. And it's really a competition between trying to compress it up to get that hotspot condition before the thing disassembles too fast. So one of the front runners for looking at the kind of research in the laboratory environment is, of course, NIF in San Francisco, which I really recommend everybody to visit. I feel they've had a bit of a bad rap recently because they didn't quite achieve ignition, but actually what's not been covered as much is all of the tremendous physics that came out of NIF. We really understand ICF a lot better than we did before NIF began. So it's really worthwhile doing these kinds of experiments. This is a 1.8 megajoule facility. The key, of course, is what sort of fuels are you burning? I mentioned deuterium and helium-3 for Daedalus. They chose that reaction because it was aneutronic. It turns out actually you get sort of 10% neutrons from the DD self-burn reactions. So actually it's not fully aneutronic. But you can look at other reactions, and the key is to know what the joules per gram is, the energy that's coming out of those systems. Next slide, please. So what I'm actually keen on is all of the alternative ideas to conventional hotspot drive ICF. So in the top graphic on the right, you'll see this is the direct drive ICF. That's the system where you're impinging the laser beams onto the surface of this capsule, imploding it to hotspot conditions. At NIF, what they actually use is an indirect scheme, which is you essentially put the capsule in a radiation cavity known as a hole room, and you surround it in this heat bath. And the idea is to really reduce those implosion symmetries. The hydrodynamic instabilities on the surface are a real issue for ICF. So you really want to make sure it's imploding and towards that convergent symmetry very nicely. Right at the bottom there, you've got another alternative idea, which is called fast ignition. This is the idea of basically in direct drive schemes. And one of the problems is once you've ablated that surface, you've now got this coronal cloud around the capsule, and because all of the plasma is ionized. And so you get to a point where the laser can't penetrate because the electron number density is such that it doesn't have the wavelength to penetrate. And so what happens is some of the electrons can be super thermally heated and they fire into the capsule and they can preheat it. And that's a bad thing if you're trying to really compress your system up. And so in fast ignition, the idea is to separate this hydrodynamic compression phase from the ignition phase. And so, for example, you can take a gold cone where you irradiate the tip of that cone and you produce a sea of electrons at the center, which can then heat the system when you're ready to. So yes, that's using a short pulse laser separate from a long pulse laser. What you can see in this table is a whole range of 4 options that I've mentioned: indirect drive, direct drive, shock ignition, which I haven't mentioned yet, and fast ignition. I'm actually a fan of shock ignition, and I was doing that for 6 years as part of my doctoral work. Shock ignition is a very unusual system, and it's the third graphic there on the right. It actually has a very thick ablator shell, and the idea is that the superthermal electrons won't penetrate that fuel early. What they actually do was the energy will be deposited directly into that ablator shell, and this actually acts to power amplify the system. The advantages of that is that you don't need such a high laser driver to implode the system. You can implode on a low adiabat, which helps with the implosion symmetries, and calculations show you can actually get a much higher gain. The gain goes something like, for a typical NIF capsule, 100 times the driver energy to the power of a half. So you can get, in theory, 100 times more energy out of that system if you will go to shock ignition. Shock ignition also helps for space propulsion, because one of the issues is if you're producing lots of X-rays and high neutrons from a capsule, this can irradiate the nozzle. And so with this thick ablator shell, and also using fuels like helium-3, this helps to absorb some of that energy. And you can see on that table some of the trade-offs between those. I won't go through all of them, but I'll just say, you can see it's decoupled. You can see it's got a thick ablator shell on shock ignition. And you can see it potentially produces more energy and doesn't require such a high driver energy to get that same performance. Next slide, please. So what I'm interested in doing is basically folding ICF physics a little bit into inline calculations of a spacecraft performance. So the emission profile. So you have a spacecraft, you say it's going to go to a particular destination. What is its performance in terms of its power, its specific power, jet power? How long does it take to get there? When does the stages burn? What I tend to find happens is a lot of the calculations, they're really speculative. So I really want to fold some of that ICF knowledge a little bit into the spacecraft performance. So what you can see here is one of the simple ways to analyze ICF is to break it down to a conservation of energy problem. So you've got the mechanical PDV work, which compresses the system. You've got the alpha particle deposition, which produces your helium particles deposited into the fuel. This all adds energy to the system. But then you've got the loss mechanisms, such as Bremsstrahlung emission of the radiation, and the electrons themselves will transport out of that central fuel. That all loses energy. So it's a competition between those gains and those losses in order to get that inequality to be greater than 0, to get ignition and then gain. And so you can see here a typical capsule in the diagram, and on the left is actually a typical shock ignition capsule, and you can see how thick the ablator shell is. And then you can estimate the burn fraction from that. And the burn fraction is really important, of course, because you need to know that, because you multiply that by the mass of the capsule fuel and then the energy in joules per gram to get an estimate of how much energy is actually coming out of that capsule, which you then fold into your propulsion calculation. Next slide, please. So here's just some examples. I mentioned Daedalus. There's others out there, such as in Icarus. We did a system called Ghost. So I was one of the founders of Project Icarus, you might have heard of, which is a DD fast ignition system. There's the US Naval Academy Project Longshot. That was deuterium helium-3 going to Alpha Centauri. There's a wonderful study done by Lawrence Livermore called Vista, which is really a Mars mission, but it was deuterium and tritium. And I think from memory, that was also a fast ignition system. But, I really want to kind of analyze these systems with a consistent code and on a consistent basis to get an idea for how they trade and how they're performing against each other. Next slide, please. So what you can see here is some calculations that start off, and when you start to write the code, these are some of the calculations that are in the code at the moment, which is written Fortran 95, is you start off with your logarithmic distance. You want to know where the probe is at different points, when it's dropping its fuel tanks, when it's burning its different stages, how long does it take to get there. So you roughly get an idea for where it is in its trajectory. And then, of course, you're using the Tchaikovsky rocket equation. And if you go to the next slide, I should point out that Daedalus was flyby only. What I'm really interested in is full orbital insertion systems. And then you've got here some equations just showing you again the energy in the capsule, the mass flow rate, the thrust, the jet power, the specific power, and you can estimate also the neutron production rate, such as per stage or per second. Next slide, please. And so here's, for example, is my first attempt when I started looking at Daedalus. This is written in this Fortran code. So you have some input which you put in. At the moment, the input deck is actually integrated into the program, and I want to separate those so it's more of a user code. You specify your input parameters, what your masses of different systems are, and your structural mass, your fuel mass, and so forth. Next slide, please. And then you start to calculate the performance. And so you can see here, for example, this is a Daedalus, and it's calculating what the Q value is, what a specific power. Note the specific power for the first stage, 40 megawatts per kilogram. So this is a monster of a machine. How many neutrons it's producing per second, so 10 to the 23. And so you can work out where it is and how long it takes for its burn time. And so next slide, please. And this is the first stage. And I sort of skip over this a little bit, but you can see at the moment I'm assuming the exhaust velocity, but I want that to be more of a calculated input parameter that comes directly out of the ICF performance. So at the moment you just put it in as a parameter, but what I want to get to is once I've calculated the ICF performance, it actually calculates what the exhaust velocity should be. Next slide, please. And you've got the second stage, and you can see here where it gets to. Again, Q value for second stage, 33.9. And you can look at the numbers. So essentially, my first point of call here was to try and replicate all of the Daedalus numbers because they were pretty reliable. The 13-member team, all physicists and engineers, very, very good people, spent a lot of time, 5 years, putting these reports together. And they really went to a very high level of fidelity in their analysis, like trying to build a full implosion, compression, and ignition of the capsule, for example, to work out what they were getting. So I see this as a kind of form of numerical validation. So once I'm getting their numbers, I was then happy to move on to other systems. Next slide, please. And here you can just see some more. If you go to the bottom table, so Daedalus, you've got total mass ratio of 40, final cruise velocity, for example, 12% of the speed of light, and it's competing emission in around 49.94 years. Go to the next slide. So what I then started to do was to move to other systems. So this is resolution. This is essentially like a Daedalus second stage, and but it fully reverse engine thrust, so it completely orbital inserts into the system. So this was for Project Icarus, and we were looking at 100 years mission requirement, and to accomplish this using basically full deceleration rather than just flyby. Go to the next slide. And so I started to calculate resolution, and you can see, mass ratio 23 gets to Alpha Centauri in around 100 years, which is 4.4 light years away for this mission. Next slide, please. You can see here some of the other numbers. So jet power, 1.8 terawatts, engine thrust, 0.39 meganewtons. And there's a few other things there, such as the payload to propellant ratios. These are metrics you can use to help optimize your fuel to propellant ratios. And the boost distance, all of this is specified, the neutron production rate, and there's a lot more stuff you can add into this, potentially as subroutines once you move to full user code. Next slide, please. This is just showing the second stage, jet power 1.8 terawatts. We'll just move on to the next slide, please. What I then realized is that the actual burn time for that particular system resolution was 15 years, which I thought just wasn't going to work. I mean, there's no way a nozzle was going to take, this was 150 hertz pulse frequency for this particular system, that it was going to take this, this kind of heat over 15 years and without leading to failure and fatigue of that nozzle. So I started to parallelize the thrust profile. What you can essentially see here is a Quintec engine system based on Saturn V, just for fun. And this is called Endeavour. And this helped to reduce the burn profile to about 3 years, which was great. But one of the problems is, particularly with that central nozzle, they're all burning these capsules, deuterium and helium-3 in this particular example. But what happens is you've got a lot of high-energy neutrons and X-rays, bromstrahlen coming out, which heats those nozzles. And so really what you want is looking at very clever capsule designs, which is what shock ignition does, because you have the helium in the fuel, which helps to absorb those neutrons, but you also have this very thick ablator shell. So this all helps with the capture of that energy, but also you can add insulation layers and then radiation shielding. And all of this can be folded into the coding potentially. But what I realized is I need to move to a four-stage parallel thrust engine system. So we go to the next slide. And this is Pegasus, which is what I'm looking at the moment. So this is 4 engine bells, and it's basically a successor to Daedalus. This is all in this Fortran code. So what I'm essentially trying to do is build these input decks up and improve the models. and then start to apply it to other systems in the literature. And the idea is to come up with much more reliable estimates for what, you know, some of the straw man studies for fusion ICF-based systems claim that they would actually do, to put them on a consistent basis. Next slide, please. So what you can see here is the green line is essentially what I'm doing right now, which is the input vehicle configuration. So you put in your input parameters, such as your masses, and your exhaust velocities and so forth. And then it calculates the full kind of trajectory and gives you all the information, all the propulsion information that you need. But what's needed is this ignition system, this ICF parameters. So that's the red line, which is what I'm sort of trying to work on. I started this project in 2013, and I haven't really been working on it much since. But I recently picked it up, hence what led to the I-squared grants. So the goal is to produce a system integrated programming tool for the purpose of calculating spacecraft mission profile and performance for ICF-driven designs. In theory, if I do this right and I build it in a modular way, sort of subroutines, I see the potential to building other options, like, for example, antimatter catalyzed fusion systems. There's lots of ideas such as Penn State University AIM-STAR and ICANN 2, which I'd like to look at. So in theory, these could be folded in, and then you could actually put, you know, try to model all these vehicles in the literature and try and get a sense for, you know, what's credible. And my hope is that this would either show up deficiencies in the coding, which would lead to an improved coding model, or it would show up deficiencies in the literature, which would lead to improved models. So that's the goal that I'm trying to get to. And here you can see the rough schedule, which is, at the moment is kind of a deep dive back into ICF textbooks, because I haven't been looking at it. I've actually spent the last couple of years on laser-driven systems, working with breakthrough initiatives. I should say the code I wrote actually also has a particle bombardment module built into it. I actually calculated not only for Daedalus and all these other systems, but also for Starshot, what the due to the dust in the ISM and the ions, what the shielding requirements would be, how many sort of grams per second was being eroded from the system. So there's lots of other things you can add to it. It's even got other things like a mag cell and a Medusa cell programmed into the coding. But for now, I'm going to strip all that out and just focus on the propulsion element. So I really want to get back to doing the coding again and regenerate the coding, which I've actually started to do already. And then I need to restructure it, because when I first did it, it was really just for me to kind of solve these problems and try and come up with better designs for the systems I was looking at. But if I'm going to make this accessible to other people, it needs to be more like a user code. And so it needs a manual, which I've already started work on. This is all written in LaTeX, a really high profile manual to go with the coding to help people sort of understand all of the equations and algorithms that have gone into it. And to increase the options, not only for the different types of ICF schemes, but also perhaps other parameters that one could bring into it. To make sure I get good agreement with some of the more reliable systems out there, such as Daedalus and the Lawrence Livermore Vista programs, which I think are quite reliable. And some of the others, like the US Naval Academy Longshot, has some deficiencies in that design, not surprisingly because it was performed by students. So, you know, I'd like to kind of rerun those numbers and find the corrections to that design, and then produce a set of baseline case models. So I can imagine sort of a whole bunch of input decks for different designs that people can actually run themselves. So all you need is a Fortran compiler, and you could run these, and then you could change the parameters yourself. And then, of course, write this up, present it at the meeting next year if all goes ahead. So that's what I'm working on. And one of the things I think I need to get to is, if you're really going to model ICF, you really need to move to full computational modeling of that system. So I used to do a lot of modeling in Vlasov solver codes and sort of high fidelity physics codes, hydrodynamic thermonuclear nuclear codes. And that's what's really needed to model these systems. But, you know, I probably can't get access to those right now. But in principle, at a later date, as an add-on to this project, I think I could, you know, that was in my original proposal, was to actually do that meshing to produce, you know, a CFL with a CFL criteria, have this capsule actually modeled in line with the calculation. And so you see the whole thing collapse hydrodynamically, implode, ignite, disassemble. And then this is iterated X number of times per second. And so you'd actually see the propulsion system and the whole vehicle moving in line with that calculation. And I think that would be much more interesting, because you could do other things as well, like change the pulse frequency, or tweak some of the other parameters to see how that affects the performance of the mission. But that's really, I think, outside of the scope of this current grant schedule. But that's where I want to get to. So that's it, and I'll take any questions later. Thank you.
Thank you, Kelvin. Appreciate it. You didn't get to the frog. You were close. Okay. All right. Next up, we have another fusion concept from Setthivoine You from Felicity. Give me just a second, and I'll switch charts here. So Set, I have your charts up, and I see you're off of mute. You have the con, sir.
That's great. Thank you very much. Thanks, Sonny. Well, first of all, hello to everyone, and then thank you to Limitless Space for their really generous support and for this, wonderful opportunity to meet everyone and to present our project. I'd like to acknowledge that this project team is actually part of a much larger team that is developing this new fusion concept. It includes Swarthmore College, University of Wisconsin, NASA JPL, University of Tokyo, the French TNRS. Other parts of this larger project have been and are currently supported by the DOE. In this talk, I'll introduce the context and the fusion concept and so on. But the overall goal of this project is to develop a realistic and practical model for one of the components of this fusion propulsion concept, the peristaltic magnetic compression nozzle system, which we would like to couple to our ongoing MHD simulations and to allow us to get the engineering drawings for the laboratory version that we're building in the laboratory at the moment. We're gearing up to build a proof of concept for this fusion concept. Next slide, please. So the concept we call for short the helicity drive. It'll come a little bit more obvious a little bit later. It's a magneto-inertial fusion propulsion concept. It exploits magnetic reconnection heating and a modest peristaltic magnetic compression system to control the temperature and density of self-stable magnetized plasma plectronemic configuration, all the way to net energy gain, during a short pulse. Plectroneme is ancient Greek for twisted thread. It's a shorthand for a recently discovered double helical magnetic state. That's a cousin of the donut-like spheromac, related to reverse field pinches as well, more donut-like magnetic configurations. The result overall is a simplified design with a really nice favorable triple product scaling. There's no auxiliary heating systems, no dynamic compression liners. You reduce the magnetic compression challenges, and we can independently control density and temperature and magnetic energy to compensate for the uncertainties in confinement time during the scaling, purely from the actual design setup. The primary end result is a unique ability to merge an arbitrary number, effectively an arbitrary number of these plectronemes, not just two compact toroids like other magneto-inertial fusion concepts you might have seen. Our preliminary calculations show that the power output, the triple product and the power output scales with the number of plectronemes raised to the power 3/2. It's nonlinear and goes up. So it provides a really reasonably simple way to increase the fusion gain without increasing the individual plasma gun specifications. It reduces the engineering challenges of the reactor concept. And you can think of an analogy as the number of pistons in a car engine. In conventional fusion concepts, if you want to increase the power, you effectively have just one cylinder and you want to increase the size of the cylinder effectively. In our case, we keep the cylinder fixed, which makes engineering challenges easier to address, and then just increase the number of pistons effectively. Furthermore, the temperature rise from reconnection heating, which I'll describe a bit later, it doesn't depend on the number of plectonemes that we merge. The density scales with the number of plectonemes, and the magnetic energy content scales as the square root of the number of plectonemes. Putting it all together to get the triple product shows roughly heuristically why the fusion product scales with n to the 3 halves. And it allows us from an initial design to compensate for the uncertainty. The number one uncertainty of any confinement system is the actual confinement time. The diagrams here show schematically the salient features of the concept. So the plasma guns at the back, you can choose a number of them that will produce these plectonemic magnetic configurations that will merge together at the throat of the magnetic nozzle, merge together, reconnect to fusion conditions, and get compressed further, and then eject out the back. And I'll describe the process in a little bit more detail. So the 3 ingredients, let's start with the first one, is magnetic reconnection heating. Magnetic reconnection is a natural phenomenon that exists throughout the universe and in the laboratory, and it rearranges magnetic field lines when several magnetic objects come into contact. The schematic in panel A here shows roughly 2 magnetized objects that come into contact, and under certain circumstances, the magnetic field lines can actually splice, reconnect, and form a single object.
Hey, Seth, this is Sunny. Which slide are you on?
Sorry, the next slide, please.
Yeah. Okay. Well, I'm synced with you now, right?
Yes, yes. Sorry. So panel A actually shows a schematic of what a magnetic reconnection would look like when you have 2 magnetized objects that come into contact, and under certain conditions, the magnetic field lines can splice together and form a single magnetized object. And what's really interesting is that part of the magnetic energy that's been dissipated during the reconnection process is very, very efficiently transformed into plasma heating. So that's been observed in the laboratory. We've done many experiments around the world, at University of Tokyo, where I was before, over in the UK at the Culham Laboratories, or over at Princeton, and so on, and Swarthmore College, which is part of our team as well. The panel B shows the database of the actual rise in temperature, so the heating that you get for a given initial magnetic energy in the actual initial objects. So here it's a fraction of that energy, it's the reconnected magnetic field strength. And you can see that the scaling is really nice. You can start reaching kilovolt temperatures, which is the beginning of the fusion temperatures. It becomes interesting, purely from reconnecting 2 magnetized objects. So there's a very interesting experiment over at the Culham by Tokamak Energy, which is a spin-off of the Tokamak of the Culham Science Center, where they merged 2 tokamaks at high fields to be able to reach 2.3 kilo electron volts. They announced that last year, purely from reconnection heating. They want to use it as a startup to get into the alpha heating regime before they bring on the other types of steady state heating systems. So that's very interesting. What we're doing is, in the blue box, we're trying to do the same thing, but at higher densities, because for a fusion concept, particularly in a magneto-inertial fusion concept, you also want to raise the density. So we want to do the same kind of concept and then raise the density, and we're preparing to build an experiment to do this. So this key challenge to reach high temperatures in any fusion concept, really. Traditionally, the heating for fusion comes of 1 or 4 types, and sometimes they're used in combination. So it's ohmic heating, resistivity, or viscosity, so collisions between particles. Radio frequency heating, so resonant heating of ions or electrons. Particle beams, so you would use charged particle beams or neutral beams, and compression of some sort, adiabatic compression or shock compression or some kind of compression method. Now, over the last decades, we've been able to understand this 5th method, magnetic reconnection heating, and harness it in the laboratory to use it. And in our case, we use it in combination with adiabatic compression, magnetic adiabatic compression, be able to preheat the plasma and reduce the requirements of compression themselves. In any other, for example, a compression concept, whether it's magnitude inertial or inertial confinement using lasers, you're taking something that's very cold, a cold plasma or a cold solid pellet, and then you want to raise it all the way to the tens of kilovolts of temperature with just a single adiabatic compression system. That's a tall order. By using magnetic reconnection heating, you can already jumpstart the process. The second key ingredient is this new magnetic configuration. Thank you, sorry about that. What we call the plectonemic magnetic configuration. It's a shorthand, really. Plectonym is ancient Greek for twisted thread. You can see in panel A there a schematic of what a twisted thread looks like. And effectively, it's a twisted double helix Taylor state, for those who know about Taylor states. You can think of it as, if you've heard of spheromax, which is a donut type relaxed magnetic configuration, spheromax have been considered for fusion confinement concepts. One of the disadvantages of the spheromax is that it goes unstable beyond a certain size, and if you don't have close-fitting walls. At Swarthmore, Mike Brown did a very, very interesting experiment where he changed the size of the vacuum chamber, the flux-conserving walls that confined and had stabilized the actual spheromax. And beyond a certain aspect ratio, the spheromax tilted inside the chamber as was predicted by MHD stability theory. But what was interesting is that the spheromax didn't die. It actually reconfigured itself into this twisted double helix state. It turns out this was theoretically predicted in the 80s by applied mathematicians who were looking at the stability of spheromax, and they wrote a little paragraph in a paper in the 80s and said, oh, this is a mathematical interesting solution that looks like a double helix, but it probably has no practical applications. It turns out that it does. The spheromax, which you can think of as a donut, stuffed inside a cylinder, when the cylinder becomes large in a certain aspect ratio, turns into a double helix. So it's like taking a rubber band and then you twist it and into a long cylinder. And it's actually remarkably stable. It's remarkably stable and long living, at least as long living as a spheromax. So it is actually an very interesting object. So in panel B there, in the bottom left, you can see this is now an MHD simulation of the actual experimental results of this double helix type plectonemic configuration. And then what was also interesting is that they made two of those and then shot them at each other, and they merged together into a single double helix configuration that was hotter, demonstrating that this reconnection heating process works for this plectonemic configuration just as well as the magnetic reconnection heating for standard donuts. So the principle of reconnection heating works in all these cases. Now, what we've also done at the University of Washington is we built a separate experiment, which we call the Mochi experiment. And that's the photographs that you can see on the top and in panel C, where we formed these plasma jets from these guns. And the idea was to be able to understand the interaction between flows and magnetic fields. And what was really surprising is we independently discovered that inside these jets, we have plectonemes as well. The plasma reconfigured, relaxed, self-organized spontaneously into this very stable plectonemic configuration. And the most interesting part is that it doesn't need a close-fitting wall. We did this in a very large vacuum chamber, very far away from walls. So we have a stable plasma that has very strong plectonemic magnetic fields. It's stabilized by helical shear flow. So I think we talked earlier a little bit about shear flow stabilization of plasmas. It's stabilized because of helical shear flows. Because it doesn't have close-fitting walls, it now opens up the ability to merge more than just two. We can put 2, 3, and 4. And that's one of the two key ingredients of the fusion concept. Now, once you merge them together and then form a single plectonemic configuration that's hotter, you can start compressing it now. And We chose to use a peristaltic magnetic compression system because it is easier to make it symmetric. It's hard to make a very strong dynamic liner to implode symmetrically in 3D while shooting a plasma into a tapered magnetic nozzle is much more stable. Now, the peristaltic magnetic compression system works this way. We have just static coils. They're arranged in a certain way. They can be tapered and so on. And all the coils are connected to each other with capacitors. So the whole thing effectively looks like a transmission line, effectively. The free parameters are changing the arrangement of the coils, the tapering, the inductance, the number of turns, and so on, the radius of the coils, and all these, and then the capacitors as well. By doing that, you can vary the parameters along the axis, and by shooting a double current pulse into this transmission line, so you send a first current pulse, and then very rapidly behind it, a second current pulse. This current pulse will travel along this transmission line, and because of the changing inductive parameters, the current pulse will start to narrow and steepen and slow down. So the front of the current pulse will narrow, steepen, and slow down, while the second pulse comes in from behind, will also steepen and narrow down, and will eventually catch up to the front one. So in the frame of the plasma that would be trapped inside, you have effectively an imploding magnetic mirror field. The advantage is that this is at constant energy, which is more efficient than doing magnetic compression by increasing the coil currents electrically using external current sources. So this is a basic calculation, back of the envelope calculation in terms of how this peristaltic magnetic compression would work. We've compared this to laboratory tabletop designs that seem to show that it works quite well. And the challenge now is to put it all together, add it to the plasma guns, the merging, and then compress the whole thing all at the same time. So this is how the helicity-drive fusion concept works. It's a 4-stroke engine, the formation, the reconnection heating, the compression, and then once you get the fusion conditions, you want to mix it with propellant to be able to vary the specific impulse and thrust at a given total specific power, total thrust power, to be able to optimize it for a given trajectory. This preheat step using reconnection heating means that the compression ratio is reduced compared to various other inertial, magnitude inertial fusion concepts that compressively heat the cold plasma to fusion temperatures. The Lawson diagram on the right gives you an idea of how the operating principle works, and then we calculate effectively at each stroke the process and then the end state, and we have papers that describe all this in detail. So the concept scales very, very nicely. The advantage of this concept, sorry, next slide. Sorry. So this concept scales really, really nicely from small sizes to extra large sizes. So we've chosen several design points, S, M, L, XL, and then XL, all this for now, the calculations are done with pure deuterium fuel. One of the XL helium-3 is to replace it with deuterium helium-3 to demonstrate that the same engine with helium-3 would have even better performance if we could source enough helium-3. And then the XLE is the same as the helium-3, but with improved subsystem efficiencies. The subsystem efficiencies are chosen to be comparable to other people in the literature, just to show how much better the performance can be. We've chosen reasonably conservative subsystem efficiencies and numbers. We can go into various details, just to be as conservative as we can.
Seth, just to make sure, am I on the right slide for you?
No, next slide, actually, sorry.
Right.
Yes, sorry about that. Yes, so these are, the top right shows the various design points from small to extra large. That's the mass of the estimated mass of the systems. And we consider the mass of the systems, and we include all the energy related systems, the energy storage. For now, we're considering, if we do consider recirculation, so there's a potential of not needing recirculation. If we include recirculation right now, it's the thermoelectric generator. We're leaving to a future exercise using direct electric conversion, which would obviously be better, but we're leaving that to be a future exercise. We want to keep it reasonably conservative. We include an auxiliary power system, 100 kilowatt electric generator of some sort. We include the radiators in the mass calculations and so on and so on. The three scalings at the bottom is effectively the end result of the propulsive output. The first one on the left is the propulsion output, which is some fraction of the fusion power output. The middle one is the mass of the engine scaling. And then the right is the ratio of the two and gives you a specific power, which is the key metric for going fast in space. The propulsive power output can range from the smallest at very low gains. So we're just at, unit gains of 2 or 3, which would be the smallest minimum viable fusion engine, all the way to fully self-sustained fusion concepts where the recirculation system can account for 100% of the energy required. That's the blue lines, the L size, all the way up to the extra large size, which is the peak performance possible given these assumed parameters. We're assuming the same parameters in terms of scaling for the guns, for the coils, and so on. The only thing that's different is the number of guns that go at the bottom. This is the unique part of the scaling. It's really the number of guns. So the power output goes from the 100 kilowatt range, because we're assuming 100 kilowatt power input, all the way up to the gigawatt range, which is the interstellar class power level.
Sorry, hold on.
So I'll go on, I guess. I think I've stopped hearing the ringing. So the idea is that this concept is really, really scalable for something that is reasonably more near term, so kind of the 100 kilowatt power range, where it can work purely as a fusion augmented electric propulsion system. So you have already a power source, and then you have this fusion afterburner that will increase the output. Add some recirculation systems to improve the efficiency overall in the M size, so the red line, where then the propulsive power output can really go up, all the way to the fully self-sustained interstellar class type engines in the large range. The masses are quite.
Hey, Seth, I apologize. Sorry to interrupt. Let me just take 30 seconds to get rid of this timer. It won't stop. Sorry.
No problem.
We could just put you on mute.
Maybe he's telling me to hurry up. Well, it gives everyone time to read the charts, I guess.
When we resume, could you also comment on the right-hand state-of-the-art F1 jet engine shuttle relative to your other plots? It's quite interesting.
Absolutely, yes, I can do that.
I do apologize, guys. Apparently Microsoft has outsmarted me. The timer is on some kind of a nested loop or something, and I can't kill the application. I'm going to go back on mute for just another few seconds. I apologize. Thank you for your patience. Just a second, guys. Let me try and go to another desk real quick so we can maybe continue going, and I can keep doing what I need to do. Well, never mind. Apparently threatening to leave my desk was what I needed to do. It finally stopped after driving me insane. I sincerely apologize, Seth, about the interruption. So first off, let me get back into it. I have your charts up. I sincerely apologize for the chaos there, but sometimes challenges come our way and we just have to try and overcome them as best we can, right?
It is Microsoft after all.
Yes, yes. I was going to say, this is, I think this is me getting karma for picking on Max for so many times that I can't count it. So, Seth, I think we were, am I still on the right chart for you?
Yes, you are. Yeah.
Okay. All right.
I hope I haven't lost my train of thought or anyone. So I think I was saying that the scaling of the propulsive power goes over many orders of magnitude from something that's reasonably near term in the hundreds of kilowatt all the way to the interstellar class power levels at the larger scale. And the important point to remember is that this scales very simply with the number of plasma guns that we put in at the beginning. It's like the number of cylinders in a car engine. When you take the ratio of the power output to the mass of the engine, you get the specific power, this key metric for any kind of propulsion system. And I think the question was comparing it to the arrows on the right, where I listed a few examples of various propulsive systems. The reason I put those up is those are the typical numbers for, in terms of thrust, kilowatts, thrust power, kilowatts per kilogram. Now, the tricky part is when you go through the literature, is that depending on who you talk to, the mass, what is included in the mass or not. Thrust is reasonably okay. It's usually half m dot to v squared, but the mass is always a bit tricky. So the idea is really to show that a chemical propulsion system, for example, a Formula One car or your typical sports car, will have a propulsive power of the order of the kilowatts per kilogram if you divide the mass of the car overall, or even a little bit better if you just divide by the mass of the engine. A jet engine has tens of kilowatts per kilogram, and a shuttle engine would have hundreds of kilowatts per kilogram. they're great. They have very large specific power, but the problem with chemical engines is the duration of the acceleration to get to a given velocity is limited by the amount of mass you can carry. And it's typically limited to minutes, hours. You know, even a car, you can drive for hours, but then you need to refuel at some point. And the fuel mass that you need to carry is limited by the exhaust velocity. And the exhaust velocity, as we all know, is limited by the chemical energy. It's a fundamental limit, which is the whole point of going to plasma, to fusion, to nuclear types of energy. Now, if you take electrical energy, the state-of-the-art electric propulsion systems, and you include all the energy-related systems, so the power systems, the PMADs, the radiators, all these things, the state-of-the-art electric propulsion systems, say we have 100 kilowatt EP, would be down in the 10 to the minus 3, you know, at best 10 to the minus 2, you know, for something like GMO, for example, kilowatts per kilogram, which limits the speed at which you can achieve. However, the advantage of electrical systems, you need very little fuel because you can thrust for a very, very long time, you know, months, years, and so on. And that's where the advantage of fusion is. The blue curve shows that with fusion, and in particular in our concept, which can scale across such a wide range of specific powers, is that you can thrust for a very long time at very large specific powers, and therefore get to high velocities to go very fast and very far. Go to the next slide. Thank you. So this is a basic calculation, you know, of the potential figures of merit for interstellar missions. So the largest, so the L and the XL. You can think of the L and the XL as bracketing the minimum viable, fully self-sustained interstellar class fusion all the way to XL, which is the peak performance. And it scales effectively as a number of guns. Again, the third column is the same thing as the extra large, but using helium-3 fuel, just to demonstrate that things look even better if you could have helium-3. And then the fourth column, XLE, is the one with a bit more efficiency in some of the subsystems, just to be able to allow us to compare to previously published concepts. The numbers here are not the most important point. It's the red bars to show that the specific power from the L to the XL and all the way to the most efficient one can scale from kilowatts per kilogram all the way to 70 kilowatts per kilogram, producing megawatts of fusion power to gigawatts of fusion power at the largest scale, and including extra power for onboard systems, as many other fusion concepts do. Now, how fast can we go? The idea is if you can accelerate for 1 year constantly, it's constant acceleration, so variable ISP and so on, with a reasonable 5-ton payload in this case here. The smallest class you can get to 26 astronomical units within a year. And then the largest class, you get 200 AUs within a year. If you continue accelerating and constantly accelerate, if you could constantly accelerate for 100 years, 117 years, you would get to Proxima Centauri at the largest possible class. So the specific powers are really, really quite attractive for really fast space travel. Next slide, please. So compared to prior fusion concepts, there's been many. I've selected a few here just to show roughly where we fit in terms of compared to others. Is we kind of use symmetric compression. We have pulse rates, because it's pulse rates that are high, but at the same time, they are reasonable. We assume a 1 hertz pulse rate, while many other pulsed systems assume hundreds of hertz, tens of hertz pulse rates, which is a much harder target to achieve. 1 hertz pulse rate is possible. At even the lowest scales, we even, sub-hertz. We don't need to pulse every second. It's also easily scalable. By changing the number of guns, in the concept, it makes things much easier than just increasing, a single one. That's really one of the main advantages. Next slide, please. Now, the importance of the magnetic nozzle is the source of this project. It's the real reason behind this project, is that a lot of these calculations have assumed a various compression ratio and the various number of guns. The table shows, for example, on the left, the 2 first columns of density compression ratio of about 500. For comparison purposes, other fusion confinement concepts using compression, they want compression ratios of 10,000, 30,000, 50,000. We just want a compression ratio, say 500. It reduces the number of guns that we need to be able to get to various fusion conditions. If we reduce the compression ratio to 62 here in this case, we just need more guns. So the trade-off between the number of guns, the compression ratio, and so on will be something that needs to be done. There's input parameters, but then we need more realistic considerations. That's the focus of this project. Realistic design parameters, finite resistivity, the discrete number of coils, the shape of the coils, coupling to the plasma and the back reaction on the coils themselves. And then we need to iterate to be able to satisfy the physics requirements with the engineering constraints. Next slide, please. So our project timeline and so on, we've already started doing this, but is to develop really the numerical tools, the CAD tools, and so on, and interface with the existing numerical tools that we have to calculate the shape of the magnetic field in 3D and in its function of time with the realistic engineering and physics parameters. Once we have that, we're going to compare to our tabletop lab measurements, also get the engineering tolerances, sensitivities to various parameters, the efficiencies, and really try and get an idea of the mass budget scaling of this nozzle, which will fit back into the fusion concept eventually. We start cutting metal because we're going to also get engineering drawings and start building these kind of coils. At the moment, we're thinking of using bitter type high field coils, water-cooled copper coils, because they're good at pulse, because this is a short pulse experiment. We're also coupling it to existing ongoing numerical simulations, and we're thinking of going to hybrid and kinetic numerical simulations of the concept. We're doing this at the moment on a separate project that's funded by the DOE with Los Alamos National Lab to improve the physics fidelity and improve the detailed understanding of the plasma itself. All this will feed into the prospective fusion performance calculation and really will help us build the coil design of the coils that will fit into our phase 1 device. Because we will have the code, we will also start scaling it all the way up to the higher temperatures, the higher number of guns, all the way up to flight versions. Next slide, please. The project team, so at the moment I'm just showing the actual project team for this particular project. We're working with Caltech, Professor Paul Bellin, who actually invented the concept of peristaltic magnetic nozzle, who's a dear mentor of mine. And then Carlos Talamas at the University of Maryland, who's a good friend, and he's an expert mechanical engineer and applied physicist who's an expert in the high power magnets and various diagnostics. And all of us together have already worked for decades together and are very familiar with the concept. And I'll also serve to interface with the Los Alamos team on the numerical simulations in the currently funded project. There's Professor Mike Brown at Swarthmore looking at the merging and confinement of these plectonemes at SSX experiment. Professor John Santarius at the University of Wisconsin is helping us with the engineering concepts, the physics and mission calculations, trajectory calculations, and so on. I can mention Yasushi Ono, University of Tokyo, expert in the magnetic reconnection. Stefan Mazouf at CNRS for the propulsion and diagnostics. Slava Turishev at JPL is helping us focus on the solar gravitational lens mission application as well. The next slide gives you a Gantt chart for anyone who's interested in seeing in detail how we're planning the work in four different steps. And then to finish off, the last slide is a summary. Basically, we have this new magneto-inertial fusion propulsion concept that provides some very interesting benefits, namely scalability, simpler engineering, and really a wide range of specific powers and applications, from something that's hopefully closer term to all the way to interstellar missions. And then we have the project outline on the right there. Thank you very much for your attention. Sorry for all the issues, and I'd be happy to answer any questions.
You're muted, Sonny.
Again, problems with the organic interface and the silicon interface. I apologize, Seth, for the interruption of the timer messing up your groove. It actually created probably no less than a dozen versions of itself in the background. So I had to kind of try and delete it quicker than it could create itself. I have no idea how that happened or why I did that. So anyway, thank you for your patience. I appreciate it. We can get back on track here. Little out of schedule, but that's okay, right? Sometimes things are hard and you get curveballs and you just try and do the best you can. So thanks everybody that's watching online and in our attendee group, or we're just going to press ahead here. Next up, I think I killed it. Next up, we have Charles Chase with some work he's doing. Charles, let me pull up your presentation here. This is another presentation exploring the nature of the vacuum. So Charles, you have the con, sir.
All right, thank you.
Let me see here. We went through this yesterday. You were good with it as is. All right.
All right, so we're going to be talking about potentially generating propulsion forces from vacuum fluctuations. And this is based on an idea that Yuval and I have been collaborating on since we met at something that an advanced propulsion and energy IAP session at MIT that the Unlab held back in 2019. And so we've been thinking about this quite a while and just wanted to really say how much we appreciate LSI for sponsoring this work and for your efforts, Sonny, in pushing these sort of disruptive breakthrough technologies that maybe are difficult to get funded elsewhere. I think you're really doing an extremely valuable thing for the community that is very, very strongly needed. Next slide, please. So I thought first give a little background on us. And so, right now I'm running the Unlab with my partner, Kate McKinnon. I fairly recently retired from Lockheed Martin, where I was a senior technical fellow. The last thing I was doing there was working on what we were calling moonshots for the entire corporation, which was trying to figure out what were the most breakthrough technologies that the Lockheed Corporation had that could really make a significant difference in our strategic posture. And what I was really doing is trying to expand the Revolutionary Technology Programs group that I ran at the Skunk Works to the entire corporation itself. I was fortunate enough to be able to work on a wide range of different technologies, everything from engineered materials, metamaterials, new structural materials, to both low and high temperature plasma systems, new types of communication. I put a couple of pictures there for this is the NASA Transonic Dynamics tunnel. We did a test of a fairly large scale morphing vehicle that changed shape in flight and was completely seamless. And then, I'm also the guy that's responsible for getting Lockheed to work on fusion, on hot fusion, a new approach to fusion that we call compact fusion. And you see a little picture there of the T4B experiment with their new magnetic confinement approach. And, I've also ran a lot of programs over the years for many different agencies. Next chart, please. And so just what is the Unlab? So the Unlab is a nonprofit that we formed that is really dedicated to turning ideas into reality, especially disruptive breakthrough things that could make the planet, and our lives much better. So we really mean that when we say we're speaking for the ideas themselves. And so we take a range of actions in trying to make that happen. Everything from seeding ideas and letting other people run with it to, actually forming collaborations and teams and doing the work ourselves. So, we're always looking for new collaborations. And, the session at MIT that we held is an example of what we do to help further human understanding. Our second mission statement there, a little more difficult now through Zoom to develop those really strong collaborations or those new sort of interactions So it's a different time. And we're executing a couple of research grants now in addition to the LSI one. One is for ONR, where we're researching and identifying disruptive technologies for the Navy to go develop. And an important point here is we're focused on scientific as contrasted to engineering disruption. So are there things that we can really, change the way that things are done? And then we're also working under DARPA DSO, the QUEST program, looking at non-equilibrium vacuum fluctuation forces, team there with Stanford, Princeton, and UCLA. And some interesting work there that's come out is we've shown that gyrotropic nanoparticle that is non-reciprocal under a magnetic field, an external magnetic field. So this gyrotropic nanoparticle will start rotating on its own just based on the difference in the fluctuations in the nanoparticle versus the fluctuations outside the nanoparticle. And so, it'll start rotating, generating a torque force. And the speed is limited by vacuum friction, and a thing will start rotating up to about a terahertz frequency. So that's some interesting work that we recently did under that program there. Next slide, please. And I think Yuval is going to give a little background about himself.
Hi. So I'll barge in for 2 minutes here.
Okay.
Yuval?
We can't hear you, Yuval.
He's frozen.
He's frozen. Okay. Well, Yuval he's a professor in the aerospace engineering at Technion in Hafia. And prior to that, he was a postdoc working with John Bush on the pilot wave hydrodynamic equivalent theory, hydrodynamically inspired. And so he has a strong background in reacting flows, combustion, interacting particles, and strong in applied math, kind of pushing math to engineering or engineering to math. And and you can see a little picture there of the work that he and John Bush did in modeling a particle in a pilot wave, approach. And very interesting is that H bar K comes out of this work as like, this is a natural occurrence of modeling things with a pilot wave, which I think is a huge breakthrough. So very interesting. Next slide, please. So this is our idea here. And it's really kind of simple. It's to take an asymmetric potential. So something like a resonant tunneling diode that has a potential in it. You can see the delta EV there. And then use that the way that the wave function propagates. And what you see plotted there is a psi squared. So it's the probability. And as it goes, you could see that going through this asymmetric potential, the red lines are the resonances, that they're different from one side of the potential to the other. And we think that this is going to act on the vacuum fluctuations. And that difference clearly indicates that there is a force there. And so really the question is, will that force, that change in the wave function, how does that interact with the vacuum? And can we get the vacuum to move in a preferential direction? And so note that we are putting energy into the system to add, to generate the asymmetric potential. So there's no argument against this from a thermodynamic or conservation of energy. And you hear about a lot of ideas of pushing on the vacuum that maybe don't follow strict conservation. So, but this definitely does. And something that's really exciting to us is that these resonant tunneling diodes are something that people make for harvesting energy, other applications. And so we could potentially actually test this fairly readily, and so the objective is to come up with a design that we could test. You can go on to the next slide, please. And so what's the value proposition? Why are we doing this? Well, one is propellantless propulsion, right? So, you know, if we have to generate power, but we don't have to carry any propellant with us, we're working on the vacuum, we can enable something like limitless satellite repositioning and cross range. You know, right now satellites are really limited. They can only have a certain mission lifetime based on the amount of propellant, especially cross range. It takes a lot of energy. So that'd be a, you know, a near-term example of an application. But also potentially acceleration to light speed. You know, if you just look at Newton's law, since we're, you know, our potential maximum speed is light speed, probably limited by vacuum friction though, which is kind of interesting. We'll be working on the vacuum, but the vacuum friction, in other words, the emissions that happen off of things because they're moving through the vacuum generates a friction that will limit the ultimate speed that you could get to. Oh, there's Yuval is back. Hi. All right,
Yeah,
next
hi,
slide.
I'm sorry.
I think
yeah, exactly.
yeah, that's okay. I don't know if you wanted to add anything or.
Well, I don't know what you said, but that's fine. I'm sorry.
Oh, that's okay.
As I tried to talk, it was down. So
yes.
Go ahead. Sorry.
All right. So next slide, please. And so I just wanted to talk a little bit about what we know about the vacuum. And so these are some fairly recent experiments on vacuum fluctuations. And in the upper corner there, the interaction between vacuum fluctuations, mechanical oscillators, and superconducting quantum states or bits. That's a device that's been made by NIST where you can balance the interaction and measure the contribution of those different things. People have measured, this is Jeremy Monday now at UC Davis, has measured a torque, Casimir torque, in a liquid crystal where you have anisotropic surfaces forming the Casimir cavity, and that gives you the rotation and the torque. People have shown you can generate photons from the dynamic Casimir effect. And so this is rather than in a Casimir cavity where you're constraining the geometry, here you're really constraining time. And by having a reflection, this is in a superconducting device, and changing the reflection on the end very fast, you can actually generate real photons out of the vacuum, which is very interesting. People have made these exquisite nanomechanical showing both repulsion and attraction. Here's an example of levitation in a liquid. So it's stable levitation based on Casimir forces and exhibiting Brownian motion where the particle that they levitated moves around. And you could see the list of all the things that are attributed to the vacuum. Everything from spontaneous emission, which emits to the background, to the Casimir forces, the Lamb shift is a frequency shift, noise, generating photons, bound states in the continuum. Well, when people talk about those topologically protected things, the continuum is the vacuum. And then in chemistry and bond energy, dissociation energy, all that depends upon the 0-point energy of the bodies of the material under consideration. So a lot of experimental and engineering control of vacuum fluctuations has been shown. But if you go on to the next slide, there's still a lot that's really not known about the vacuum, which comes from the quantum ground state of the harmonic oscillator. It shows up in Planck's energy distribution. It shows up in the uncertainty principle. But there's this little issue of the cosmological constant, which according to our measurements of what we call dark energy is quite small. But if you do a QED calculation and use the Planck scale for the frequency cutoff, that's where you get the 120 orders of magnitude difference between what QED predicts for the vacuum versus what we're measuring as dark energy. And as Peter Maloney, one of the experts, he's from Los Alamos in vacuum fluctuations, he says the effects, they can be attributed either to radiation reaction or vacuum fluctuations or fields. And so what's really going on, it's the interaction between the vacuum and the material and the fluctuations in the two that's key. And you can't really say one exists without the other. They just don't. What's key is the interaction between the two. And people like to quote Jaffe, who's a physicist from MIT, and he wrote this paper showing that you can derive the Casimir effect without using vacuum fluctuations. And by the way, that was not a new result. That had already been known for 25 years or so. But you can't really derive QED without the vacuum. So we have this sort of conundrum about what's real about the vacuum or not. Next chart, please. But one thing that we do know, I think, is that in order to generate forces from vacuum fluctuations, you need to either break symmetry or be in non-equilibrium. So if you assume that the vacuum has translational and rotational symmetry and that it's in equilibrium, there's no way you can generate a force. And that argument is purely an energy argument and doesn't depend on the details of the physical model. So it doesn't really matter if you're using QED or fluctuation dissipation or world lines, which is a wonderful approach that Sunny has uncovered to looking at predicting Casimir forces. You need to either break symmetry or have a non-equilibrium system. So the asymmetric potential we have is a non-equilibrium system. And so there's no fundamental argument about generating forces. And, you can also consider that vacuum in a curved space-time doesn't have translational symmetry. And that also curved space-time is not in thermal equilibrium. Those are both true. But then also maybe the vacuum has structure, which is something that Sunny was mentioning at the start of the event. His work looking at whether there's actually structure in the vacuum and symmetry can be broken. So, but really the point is that our asymmetric potential is a non-equilibrium situation, and so we should be able to potentially generate forces. Next slide, please. And so, again, this is our asymmetric potential, and we're just this is just solving Schrodinger's equations for a resonant tunneling diode for an asymmetric potential. So it's really solid theoretically, right? There's no new physics here. It's just a new application. And you could see the sort of separations we're talking about are on the orders of tens of nanometers. And what's plotted on the right-hand side is the resonances, the propagation for both the symmetric versus the asymmetric. There's some differences there. But again, the asymmetry in psi here really indicates that there should be a propulsive force. I don't know, Yuval, did you want to add anything?
Yeah, so I just want to say that this is a very fundamental, abundant device in physics, analytical chemistry. They use the same potentials. And also in almost every single electronic devices that we use today. So, and if you think about the problem in which we do add external potential as voltage, then this whole structure, this whole nanostructure will be slanted, if you like, and then the effect will be much, much larger. And then when you apply a voltage to this structure, if we allow ourselves to do so, then we will also have some quasi-bound states on the left-hand side, which will also change the waves significantly. And if you look at resonant tunneling diodes and solution for resonant tunneling diodes back from the 70s, they are looking at the same simple potentials that we look at, and the validation for those kind of simple Schrödinger equation, time independent and time dependent solutions are very good with experimental results. So I think, but the most important thing here is both for tunneling diodes, resonant tunneling diodes at the terahertz frequencies, for example, and other applications. Physicists and in chemical and analytical chemistry, for example, they always look at the bound state or what happens between those barriers, whereas we're looking at the radiation difference.
Yeah, we're looking at what's going on downstream.
Exactly, what's going yeah, and if you think about those structures, they're really one-dimensional also. So I think this is a very, very simple but fundamental model that we can use to interact with the vacuum. The last thing I wanted to add is that I think those devices are interacting with the vacuum already. So we don't have to do it. We just have to exploit the physics here. So
yes.
And also, I just wanted to add that I'm very happy to be here. So I want to thank LSI and Sonny. It's been wonderful to work on this project and wonderful to work with you, Charles. So thank you.
Yeah. Okay, so I just had a couple of more points to make, Sonny, if you go on to the next slide. One is just looking at Planck's radiation law and as a function of frequency. And it's interesting that the vacuum fluctuation component will dominate over the thermal component at room temperature above 7 terahertz. So above 7 terahertz frequencies, the major contribution will be from vacuum fluctuations. And so, you know, and that, you know, it's about 50K down at 1.2 terahertz where, you know, there are some devices really close to those sort of, so it's interesting to consider that when we're talking about moving the vacuum. Next slide, please. And this is just a partial list of some of the diodes or asymmetric potentials basically that are out there. And I just, you know, the one interesting one to highlight is from our friends at Sandia, Paul Davids and David Peters. That's the one on the bottom. They recently published this in Science, and it is a diode operating up at 1 terahertz at using for low-grade heat energy harvesting, you know, to get the electrons across. And it's a photon-assisted sort of approach. So that's a really promising diode for our application, I think, that people are making. Next slide. And I think we're out of time, right, Sonny? So, you know, these are our objectives is to, of course, the primary objective is the space propulsion not limited by propellant with potentially these large accelerations. And we want to generate forces by engineering the direct interaction between vacuum fluctuations and the fields across asymmetric potentials. And so you guys can read that. Next chart, which is just our milestones. So I think we have a pretty good laid out program to accomplish this. And I think that's, don't want to go too much over time. Next slide. And so we really believe in unlimited abundance. I think that, you know, everything that here on, we've been able to create so much, there shouldn't be, I don't believe there's a limit to what we can create. And so I think like this group here, you know, there's I think abundance is unlimited. I just wanted to end with that thought. Thank you.
Thank you. Thank you, Charles. Thank you, Yuval. I appreciate it. And Yuval, thank you for continuing to fight against the computer that tries to take this meeting offline, right? So,
sorry about that. Yeah.
Oh no, no worries. I was going to say it's we just keep chipping away, right? So, all right, let me switch gears here. Go to our last talk of the day. Remo, I'm pulling up your slides.
Here I am. Okay.
Okay, and your slides up. Just remember to tell me to advance the slides.
Why can't you use the PDF? I think it is more because okay, it's going. No, it's okay, it's okay. Can you begin?
Yeah, you have the con, sir. Just tell me when.
Okay. Okay. Good evening. For me, it's night, more or less. No, not yet, but it's almost 8 p.m. But okay, what I want to tell you is something about traversable wormholes in this context of the interstellar exploration. And to go on, I asked Sonny to exactly. This is the slide is quite old. Kelvin is the artist of this slide. Is has been done in 2007. This is was the first time we met about to talk about interstellar travel. It was a warp drive workshop in London, and I'm going to use this table to show you what is the history and the proposal for the future of the propulsion systems that we are going to think. So the past is represented by the Apollo mission and so on. As you can see, if c is the speed of light, we started from a very, very small percentage with respect to the speed of light. And the future should be something that approaches the speed of light, thinking of something that is pure thought on rocket at 19% of the speed of light. We see from the self-limiting technology that the special relativity gives you a big problem about the mass of your spacecraft that continue to increase, and it's everything about energy, that you need more energy and more mass and so on. Next slide, please. Okay, and so the big barrier is the speed of light. This is a fundamental constraint that in the framework of special relativity, you cannot do anything. So the problem is that from one side that the tachyons are not yet detected. So, okay, sure. Okay, Kelvin, okay. But this doesn't matter. It is only a way of presenting the problem. But if we continue to insist to thinking about spacecraft, in this framework are under the law of special relativity. So we have to pass exactly this kind of a constraint of the speed of light. Otherwise, every mission, every travel into the deep space can be a one-way travel. So this must be clear, really clear. So the only proposal that we can manage, except the warp drive, is traversable wormholes. Why? Why? Because traversable wormholes are a solution of the Einstein field equation. Next slide, please. Okay, what is a traversable wormhole? This is predicted by GR, if you want. One example of the traversable wormhole is the Schwarzschild solution that is also used as a model to represent a black hole. Unfortunately, the Schwarzschild wormhole is highly unstable, and so there is no possibility to use it to have a shortcut between one point in space and time and the other one. So the tentative to use the Schwarzschild is completely a failure. Well, the problem is that in any case, the Schwarzschild wormhole represents a model, a pioneering model, a model to think about a possible shortcut in space and time. So as you can see from in this picture, there is a concentration of a bizarre thing. This is the negative energy. Next, please. Well, other things, as you can see from in this slide, there is a metric. A metric is a fundamental object for GR. This is a spherical symmetric metric. There is a sphere, the last two pieces, and attached to these spheres there is something that is depending on a function of the radius. This is called the shape function, and another function that is the redshift function. So if you put the radial part equal to the time part, you obtain and B over is a constant, you obtain exactly the Schwarzschild solution. But the Schwarzschild is not very useful for us. So the idea is imagine which kind of B over R and phi over R can use to obtain something that is traversable. So this is the recipe we can try to think. In this way, if you try to model B of R and phi of R, sorry, then you can have information about your stress and energy tensor. So in particular, the energy density, the radial pressure, and the transverse pressure. Next, please. Well, these are the Einstein field equation, very, very simplified in an orthonormal frame. So we are in a spherical symmetric framework. The first equation gives you a relationship between the energy density rho, that can be anything you want, and the shape function. So if you give a gas for the shape function, you can have an output on the energy density and vice versa. So if you have some energy density, you can deduce exactly the form of the shape function. A desirable traversable wormhole has no redshift, so phi of R must be a constant or something like that. In this way, the possibility of having redshift is completely cancelled. The last equation is, if you want the expression of the stress energy conservation imposed by the general relativity Einstein field equation, if you want. So to have a traversable wormhole, you need something very strange called exotic energy. So this exotic energy is, if you want, this energy, it must be negative in some and violates the null energy condition, the strong energy condition, and weak energy. So all the energy conditions are violated. This must be concentrated very close to the throat, something very similar to the horizon of black hole. And at the moment, the only candidate for the for having a negative energy is the Casimir energy. Why? Because this can be reproduced in the laboratory. Next, please. What is the Casimir energy? Casimir energy is related to the Casimir effect. It is very simple. You have two plates. These two plates are parallel at zero temperature. This is the very idealistic possibility that you are in which you obtain the result E divided the energy density is minus pi squared divided by 720 and then a to the fourth. A to the fourth is exactly the separation between the plates. So as you can see, this is a very tiny force, and this force is more or less 10 to the minus 7 Newton when you adopt 1 centimeter and 1 micrometer of separation. The effect is due to pure, okay, there is a way of thinking that maybe this could be a pure relativistic effect. This is the school of above Jaffe, as mentioned by the previous speaker. But there is this subject is highly controversial, and so the other way of thinking is that this is generated by pure quantum fluctuations. This effect is an effect generated by boundary conditions. So if you change the form of the plates, you obtain another result. For example, if you have spherical boundaries, you obtain a positive. This is a result due to Gary Barton. I want to draw your attention to the form of the stress energy tensor. This is a traceless. If you compute exactly the trace of this stress energy tensor, this is without trace. This is a property of the electromagnetic field. This is very important. Not only this is a property, the other property is that the energy momentum tensor is conserved. So this kind of effect arises because you subtract two kind of infinite vacuum energy, and the result is finite. There are a lot of techniques to obtain this number, and there are many differences about the kind of calculation you can use. For example, you can use heat kernel, zeta function, and so on. A lot of things. Also, simply a cutoff and so on. And at the end, you obtain a number that is consistent. The next one, please. Okay, but in the literature that try to connect the Casimir energy and the traversable wormhole, you can see that if you can take seriously this kind of source, there are few publications. One is the very famous paper about Moritz Thorne and Yortsever. You can find the discussion about the Casimir energy usage inside. This is physical regulators. And the other is the book of Matt Visser. There is a calculation that he tries also to use a more realistic model, including also the mass of the plates, that gives you a positive contribution to the negative energy. And so one of the technical problem is exactly this one, the compensation of the massive the mass of the plates, but must be overpassed by negativity. So in a sense, we need more negativity than with respect to the mass of the plates. And at the moment, since the experiment use very, very thin plates, something in this direction can be done. So if we apply the first Einstein equation that I showed you before, and integrate from the throat, the position of the throat that is represented by R0 to a certain distance from the throat, you obtain this the form of the solution that is obtained thinking that the energy density is constant. In this way, you can see that the shape function is not asymptotically flat. This means that when R is very large, the shape function goes to infinity. Well, at this point, the problem is that if we desire to have asymptotically flat traversable wormholes, this situation is not very useful. We have to translate this result and try to keep also the relationship between the radial pressure, the famous number 3, and the energy density. So these 3 must be preserved in some way. Next, please. So if we abandon the separation of the, so if we think that the separation of the plates are not more fixed, we can obtain a result. This is a very new result because the form of the shape function is a mixture, if you want, between a constant 2 divided by 3 R0 and the other term is exactly is very similar to the Ellis-Brownnikov wormhole. Is a superposition of this, and moreover, in this way, the with the omega equal 3, that is obtained by imposing an equation of state that relates the radial pressure and the energy density, preserving the number 3, so the relationship between them is exactly of the Casimir type. You obtain a solution that is completely new, but unfortunately, the solution is of the Planckian size. So what we obtain is a traversable wormhole that is traversable in principle, but not in practice. But this is a good news in any case, because in some way, you can build a relationship between the Casimir energy and the traversability of a wormhole. Pay attention also to the ratio between R0 and R1. R1 is directly connected to the Casimir device, and R0 is usually is a free parameter, but if you force this ratio to be 3, you obtain a solution that usually it is impossible to obtain. The stress energy tensor is partially reproduces the original Casimir stress energy tensor, because there is an extra factor that works exactly on the transfer pressure. Next, please. The other possibility is take advantage of the first solution and try to see what happens if we try to connect the first solution, the Cassibry, the first part with the parameter alpha, an exponent, and the original solution that I have presented before, so the R square. In this way, as you can see, the solution with the alpha and the absurdly benign traversable wormhole that has been presented in the paper of Morris and Thorne, they have some similarity in the sense that from one point on, you can truncate and you have continuity between the inside and outside. Outside of what? Outside of this wormhole, there is the flat space, so there is nothing. So this is very good because the solution that you obtain is very, very close to something that you want to obtain. Note that close to the throat, the similarity between the solution of the with the cubic and the absurdly benign traversable wormhole is very, very close, except for the exponent 2. So in a sense, this kind of solution and this framework are intimately connected between them. The problem is that at this point, we have the opposite result. Instead of having Plancken, we have a very, very huge wormhole. Maybe this there is something non-physical, but we instead of discarding this kind of solution, we try to investigate more. Indeed, if at the moment the experimental devices are concentrated on nanometers separation plates, but if you try to use plate separation of picometers, so the next scale that is not so far, but it's not impossible, you can reduce something that and you obtain something that is as the size of 10 to 11 meters, something more reasonable. Next, please. Well, all these things are completely found connecting the semi-classical the Einstein field equation with a quantum source and a classical GR Einstein tensor. So the idea is that maybe, and this has been proved in the paper that I showed under the title, there is a relationship between the quantum fluctuation generated by the graviton of the same traversable wormhole that is able to sustain, to power exactly the throat of this wormhole. So one point exactly is to manage the original source, electromagnetic, plus this quantum fluctuating part, take it together and see what happens about the stability. Next, please. So the purpose of the research is very, very simple, because we have to manage the number and inside the circle, and the number inside the circle is connected to one simple thing. It is the plate separation, but not only, because the plate separation are multiplied by many things. Some of these things are exactly the temperature, the corrugation, the conductivity, but not only. For example, there are recent experimental results showing that if you try to use superconducting plates, you have more extra energy gain in negative sense that can help us to fine-tune the relation between the plates and the size of the wormhole. But this is the real goal. The next, please. And not only it is important, as I said before, this is also important for the warp drive, because the warp drive, in the sense of Alcubierre, needs a negative energy. So if you have a negative energy density that you can manage, you can fine tune in some way, you can use it. You can have the possibility to control the traversable wormhole throat and also the warp drive. So we have really two at the price of one. Next, please. Well, the team is myself plus another collaborator that I contacted 2 months ago. Now, a collaborator with a great experience is actually at the moment it works in Frankfurt. The idea is to submit the work to journal listed into the parentheses. Usually my papers are there, and especially the paper about traversable wormholes on classical and quantum gravity. There are one in physical level D, in EPJC, that is a good impact factor, and also in physics letters B there is something. And so the idea is to produce a paper in the first semester, and if we are lucky, maybe more than one. I do not know. It depends exactly how things sound, because usually when you try to think about it, okay, this is easy, usually you have the opposite result. Instead, when you have the something that seems to be difficult, you have something that is more fast. Many of the calculations will be done with the help of the Maple software, in particular the release 2020. And thank you for your attention. Okay, this is the outlook.
That's the objective, right?
Yep.
Hey, thank you, Remo. I appreciate it. Fantastic talk. That was all the talks for today. Let me stop sharing my screen. Okay, so we can switch into some Q&A. I know we're a little bit behind schedule. Part of that was each one of the talks has just a little bit more interesting stuff to say. And then we had a small little computer kerfuffle that conspired to try and take us off task, but we overcame it and continued on. So let's go ahead and switch into a couple questions here for the previous talks. Dylan, have you been monitoring some of the different avenues for questions?
Hi, Sunny. It's James here. I think I'm the Dylan for this round.
Ah, very good, James. Thank you, sir.
So we have a question from Max Comes, who I don't think is on the panel at the moment, but it's for Remo. What is the point at which negative Casimir energy overcomes? Hello.
Yeah, I've seen the question, and yeah, I didn't do the calculation, but this is quite simple because you have to balance exactly the positive mass and the energy, the Casimir contribution, and see in which way you can have the transition. This is one of the points, but the other points is usually the Casimir is very far from the zero temperature. It is not a 0 Kelvin. It is at some temperature, so you have to include also the effect of the final temperature. You have to include also the finite finite conductivity, but there is one point that I missed in the last one of the previous last slides, is that if you introduce also the electromagnetic field, you have also the dielectric, and the dielectric constant is the related to the so the permittivity. The permittivity in some materials, I have discussed something with Sonny before the COVID. Can have can be represented by metamaterials. Metamaterials have a property very interesting. The permittivity can be negative, and so this can be an additional point to have more negativity, and so to possibility to overpass exactly the mass that is positive. So if we add 1 point that is the superconducting, the other point that could be the metamaterial, and so on, maybe you can have something that can be managed. This could be good. This will be one of the point of this research.
Thank you, Remo. That was a good answer. James, got another question, or
we've got a question? We've got a question from YouTube.
Okay.
We have more than a dozen people watching on YouTube as well, and so Sumantro Sina has asked for Dr. Sedwick, actually. So back to the first session, I think. What is the specific power for Dr. Sedwick's engine? How far away is their device from reaching that target?
Yeah. So at this point in the first phase of the research is actually that's one of the things we're going to evaluate, because we don't have a good sense for what the total system mass is going to be, right? So those sort of target performances, I don't think are out of the question, because doing some just very preliminary mass estimates for some of the major components like the magnets, you know, I think that the values of, you know, on the order of sub kilogram per kilowatt, or, you know, tens of kilowatts per kilogram or higher are achievable, but it's all just sort of speculation at this point until we do more detailed analysis of the system.
Thank you, Ray. James, if you don't have another one, I had one I was going to field.
Go ahead.
Yeah, this question is for Richard. Richard, in the process of you kind of talking about the progression of this photonic crystal, reflective over a large bandwidth of light, what would be, like the first initial kind of demo concept you could think of that might be, I know breakthrough star shot's kind of like this endpoint, but there's a life cycle. What's in the crawl, walk, run parable, what's in your mind, what's a crawl type of thing for what you're working on?
So I think definitely one of the things that is good is that what you would like to do is make the sails as big as the wafers that are available. So that's the nice thing, because right now there aren't 4-meter wafers that we have. So probably the biggest is somewhere around 450 millimeters. So essentially what you want to do is kind of wait. You want to go with there's definitely a push already in nanotechnology to make bigger and bigger wafers. So that's always been a thing. And also for the lithography, that's also been a thing to make bigger and bigger, smaller, bigger lithography patterns with smaller features. So that's always like an endeavor for people in nanotechnology. So I think that the light sails will essentially kind of go with that push. I think on the smaller scale, I think what's interesting is to really figure out what we can do with the photonic crystal that's beyond just putting some holes in a membrane, and really trying to see if you can get some more functionality out of such a very minimal material, because you're really trying to push the limit in how small you can make this thing. I think another challenge will probably start to be stability. Like once you start to make these things really big, you're really thinking about, if you're thinking about a 4 by 4 meter sail of this material, it's essentially like making a 4 by 4 meters bubble. But now consider that the bubble is completely covered with holes at the nanoscale. So it's even more delicate than a bubble, right? And when I say delicate, the first thing people will say, well, how can you propel this thing to really high speeds? But I think it's delicate depending on how you push it and how you put the radiation pressure on it. So if you do it evenly or in a very engineered way, I think you can do it. Does that answer the question?
Yeah, no, that helps me understand what you anticipate some of the next steps would be, right? So
yeah. But definitely, sorry, go ahead. Yeah.
No, finish, please.
No, but definitely, I think as far as going to the wafer scale, we've been able to show that. It's just a matter of now just cost and time and how much it takes to lithographically make these small patterns. Even a large array like this is very, very difficult over a large size. So.
James, to you.
I was just going to ask if we had time for one more question.
Yeah, maybe like 2 or 3 more at most, right?
Okay, great. We have a question from Michael Rowlands, who's watching on YouTube, for Remo again. And the question is, can you see it? If interatom spacing in a material is on the order of 0.1 nanometers, what is a possible way of holding conductors 0.001 nanometers apart?
Could you repeat, please?
Of course. If interatom spacing in a material is on the order of 0.1 nanometers, what is the possible way of holding conductors 0.001 nanometers apart?
Yeah. At this level, my answer is I do not know. Absolutely, I do not know.
Okay.
That actually sounds like an interesting question. It'd be nice to pass that on to Jim Jimzewski at UCLA, Charles. I know he routinely does things like drawing pictures with atoms, right? So in terms of something that somebody that's used to seeing numbers like that, he wouldn't pass out with that kind of a question, right? So.
Right. Yep. Yeah, right now he's building an AFM that is a single molecule at the tip and using it to do atomic manufacturing, where he can place the atom on other atoms exactly where they want them. So that's what he's working at right now.
Sounds more than a little tedious. A lot more challenging than dealing with a wayward timer on a computer, right?
Yeah.
So one question for you, Charles, on your guys' work with the asymmetric potential. Do you anticipate there's a possibility that the force capability of that will be better than maybe better than a photon rocket?
Yeah, so I do, but one of the primary objectives of the first part of our study is to calculate the force from one of these simple asymmetric potentials. Mm-hmm. And then it's a question of, surface area, material properties, and also coupling. Can we envision coupling these together and potentially in a coherent way by using a stipulant, some resonance or noise-induced coherence or an approach like that to drive them all into a coherent behavior, which maybe we'll be able to get larger forces that way. So, but that's part of our study is to figure that out.
Okay, great. That's fantastic. James, if you have one more, go ahead. Otherwise, I'll finish up with one last question.
No, over to you.
Okay. All right. Just a question, Kelvin. You've been looking and thinking and considering fusion for a lot longer than I have. In your estimation of the field, or what are some of the favorite concepts that you've seen discussed over the last 10 years? I know we had some today in the telecom and so forth, but I'm just curious to hear, what's your Reader's Digest thought process on the forecast?
So who were you addressing that to, Sonny?
Kelvin Long.
Hi, Sonny. I'm not sure it's true. I've been thinking about this longer than you, but I think I'm younger than you. I think, I mean, obviously I've gone down the inertial confinement fusion route because that's where my former job, I dabbled in that area. And also my doctoral work was in that area. So I ended up going down that area, and I think it's credible for the future. But I've always been a big fan of Robert Bussard's work, and I don't mean the ramjet, which I love. I mean his electrostatic polywell kind of concepts, and I think that's something that probably should be looked at a bit more. And I know there was some studies going on a couple of years ago, possibly US Navy, I think, and that's something that's always got my interest. But the fusion is still so much we don't understand about the operational ability to make fusion happen in a laboratory. When we switched NIF on, we discovered a whole load of physics issues with scattering mechanisms and things which we didn't even know existed, and that's always a problem, I think, when you go into high energy propulsion systems. In particular, if you're trying to scale up something from a laboratory to something that's much higher energy or much higher power, I worry about that scaling, whether it's always appropriate, because you get these extra physics that comes into play. I won't say I have a favorite, because I'm not sure that advocation is the right way forward, but I think that inertial confinement fusion, I think, has great potential. But obviously magnetic fusion and some of the concepts we've heard today have great potential. And I think that whatever makes it happen is great. So I'm a fan of all of them in some ways.
Okay.
I had a question for Charles, actually, if I could very quickly ask it. I didn't quite understand the source of the asymmetric distribution and when you solved the Schrodinger equation, and you had this asymmetric distribution inside the boundary conditions of the potential. What's the cause of that asymmetry?
Do you want to address that, Yuval?
Yeah, sure. So basically, the asymmetric barrier reflects different waves. I mean, the problem is actually coupled. So each region within this structure is coupled to the other one. So when you solve this Schrodinger equation, you should actually take into account every boundary condition, and the resonant tunneling is also affecting the outside wave. So the asymmetric potential is actually reflecting backwards to different sizes in a different asymmetric manner. So that's the way you get asymmetric radiation coming out of this whole structure.
Yeah, maybe I'm misremembering. I go back to my college days. I remember solving Schrodinger equation for spontaneous fission type problems, and I don't remember seeing an asymmetry in the distribution. But you're saying there is.
Yes, there is. So usually, by the way, yeah. Go ahead. Sorry.
Yeah, maybe I've misremembered it. That's okay. Yeah.
Yeah. So usually, in textbook problems, usually what you see, and it's also true for electronic devices, what you see is a symmetric double barrier, whereas in our case we actually take the structure to be asymmetric in the first place. So that's one reason for seeing those asymmetric waves reflecting outside of this structure. The other reason we will get some asymmetric forces and waves radiating is the fact that when you apply a potential to the structure, the whole structure, the whole potential of the whole structure will be slanted in a way that in a high potential region, there will be the waves will be much increased than in the low potential regions. And so if you solve this problem, you will immediately see that in the low potential regions, you'll get almost no waves radiating out of this structure, whereas on the other side, you'll get much prominent wave structure.
Yeah, Kelvin, I think you almost channeled Geoffrey Landis. He had a question. I'm just going to read it. I think part of Yuval's narrative there answers it. I am puzzled by the asymmetric potential. In the figure, the vacuum potential is higher on the left side than on the right. I do not see that this is possible. So I don't know if there's any additional words you want to add, Yuval or Charles.
Well, you know, these kind of results are fairly well known in resonant tunneling diode work. And, you know, I think we didn't show any of the validation data of our predictions. That was one thing we regretted that we don't have yet, or we don't have charted up yet. But, you know, we're going to replicate some of the published results. So, you know, there are published results that show that. So this is not a unique, brand new thing. Would you, anything to add to that, Yuval?
Yes, so you can see such structures, wave structures, and both electronic devices, but also in molecular dynamics and waves in between molecules. So so there are similar structures which are asymmetric. That they solve in analytical chemistry, for example. So, and they are published. So we can definitely count on these kind of structures as for our validation. So we're pretty sure there are such asymmetric potentials.
Thank you, Yuval. Thank you, Charles. I think I'll just open it up to the panel. Do you guys have any questions for each other or anything like that? We can finish with that.
Hey, I've got a question, comment for Yuval.
Sonny, can I make 2 comments or not?
Stand by, Remo. I think John just barely beat you to the button.
Okay. Yeah. So Yuval, I like that resonant tunneling diode. Have you thought about doing? You know, that's something that we could look at with HQA, right? Because we've done a lot of tunneling experiments, and we have now a numerical simulation which allows us to treat arbitrary topography. So it is something. Is the idea there that you by tuning the space between these asymmetric barriers, you basically enhance the asymmetry and so the net force? I mean, is that the idea?
Well, not exactly. It's so the idea is to tune the potentials, right?
Okay, so
so that you will have.
Okay.
Yeah.
Yeah, the height of the potentials, but you also have the distance between them, and it doesn't.
Exactly.
The distance doesn't matter. Or it does.
Well, it doesn't really matter, and theoretically, because you can. Of course, it matters for the electronic devices, but if you look at different distances between those barriers, you'll get different resonant terms. Either
Right.
smaller or larger. So you can definitely tune those, and they do that in resonant tunneling diodes to get the specific frequency. For example, for 7 terahertz or for 1 terahertz, they do get it's only a distance of a few nanometers, maybe less.
Right, because in ours, everything would have resonance when the distance between these 2 barriers was an integer multiple of half the Faraday wavelength, right? And so
exactly. So in your case, by the way, you can also induce some bottom topography to change the potential. So you can do a lot with the HQA. I thought about it also, and basically you can tune the difference between those barriers. So that you will get resonant in the Faraday wavelength, But in our case, we just imagine that we have all kinds of energies in the vacuum. So we solve for multiple modes. So that's a picture that Charles showing you. So we have multiple infinite number of modes that you can realize there. So that's why you will get resonant anyways, right? For each mode.
Imagine, I mean, in terms of particles, the idea would be you'd have particles coming in from left and right with equal probability. They would be going out in another direction with a preferred direction, and the asymmetry would depend on the spacing of the barriers and the depth of the difference in the depth of the barriers. So yeah, that's something that one could definitely do with HQ. We were doing similar things. We're looking at super radiance, which is two particles interacting in sort of connected cavities. And so we have them, like the mathematical formalism is in place. So we can talk about this offline next time we chat.
No problem.
Right. Yep. Great discussion. Remo, I think you had a question.
I sent two messages. One was about the squeeze state to use for having an extra contribution to negative energy density. Well, about this point, there are some papers of Larry Ford appeared on Physical Review D, but 1 year ago, I talked to a group of people working on experimental physics, and they said that they're completely absurd. This is a nonsense, and so I am in the middle of 2 points. One, the theoretical point is very good. They say it is very good. Some experimentalists, they say that it is ill-posed. And so at the moment, maybe in some future, there will be investigation about this possibility to use squeeze states because we have lasers. So with the laser, we can do many things. The other thing is about the nanoscale. I saw the question once again about the numbers. Well, once again, I have to refer to some friends of mine that works directly on Cassibry effect. I take the occasion to tell you that there is a group in Sardinia where they are trying to weight the vacuum. So in a sense, they try to apply the Archimedes principle to see if the vacuum levitated or not, because if this is negative, so in a sense you have less vacuum, so there is something that is different. And they use a very specific technology, and maybe, I think maybe, they can give me some answer about nanometers or some very small devices. Actually, this is a problem of experimental physics. And a comment to if it is possible, to Charlie Chase. I'm very curious about the asymmetric potential. In a sense, could it be possible to extract some Casimir-like effect? I mean, something that is negative, in a sense that not because you have a simple difference between one that is as a value, another it is negative, and so the difference is more negative, not in this sense, but something that if you try to manage with the potential, with the barrier, and the output is can be negative in a sense, because you have this wave that are more compressed or less compressed, and so the psi square, the probability of the wave function, can give you something that at the end it can be negative and so you have something like Casimir.
Yeah, so along those lines, some work that Sonny did using the world line approach to modeling Casimir forces, which is it's based on a string theory QED, so it's a very valid approach, and it clearly shows negative vacuum pressures in Casimir cavities. So, you know, but there's a question, you know, and the model models Casimir forces very well, and it can handle arbitrary geometries. Now, I don't know if using that approach, you can add potentials to the surfaces that you're modeling. And that would be a way to looking at these asymmetric potentials to even increase that negative vacuum pressure that the Worldline approach shows. Now, whether that's actually real or not, I think that's something Sonny is in one of his experiments is trying to figure out, is there really that there? And I think, so it's very exciting. I hope I answered your question.
Yeah, just for the folks that are online, we didn't go into too much into the work that we're doing. There are other talks available online where I do go into that. So there's a little bit more detail out there associated with the numeric Worldline approach to calculating the Casimir phenomena in terms of understanding if there's topology structure to the quantum vacuum and some of these arbitrarily shaped geometries. So, but back to you guys, questions for each other or anything? Okay, well, let me go ahead and wrap us up. You know, just let me loop back to what I said at the very beginning. I just want to thank all of you folks for joining us today, right? Both the presenters and the folks that are online that have taken some time out of their schedule to engage with us on this stuff. So for the presenters, thank you for joining me. I know we were early in the morning for the West Coast, very, very late in the evening for you all. I know it's like midnight outside there for you, a little bit past. So thank you everybody for giving me some time and going through your talks. It's been very, very interesting and fascinating. I've enjoyed every minute of it, and certainly appreciate a little bit of patience when we had a weird computer kerfuffle, but we got through that. I think, I just want to finish with a couple of things. Richard, you said something in your talk that just kind of jumped out to me, and it's more of the emotional side than the technical side. And it had to do with when you were first looking at some of the objectives of Breakthrough Starshot in terms of the size of things and what the characteristics might be. Your initial thought process is, wow, how are we going to get there? I mean, we're here, right? But just in the process of having thought about it personally and working on it and thinking about it, you've managed to kind of think of some different ways where you can start to make, progress, at least some type of true measurable progress of trying to get from, I don't know how we're going to do it, to, hey, we did it, right? You're in a different place now, but it took you to start thinking about it, right? To challenge yourself to figure out how can we solve these problems, even though they may seem completely intractable. So that really kind of resonated with me, right? And here you've seen in your brief period making something the size of a grain of sand, grain of salt rather, to something that's bigger than, or at least as big as your iPhone, at least anyway, in terms of, cross sections. So that's kind of a neat story. And I think something else from one of the presentations, again, just kind of picking on the emotional part there. Jason, in your talk, you had that neat picture of a gentleman that was giving of his time and energy to come help you guys in the lab. He's an 84-year-old gentleman, Alan Davis, I believe you said was his name, right? And it's neat to see you guys doing things together that way. And I think that's an important thing for two aspects. You're doing things together, but you're doing things across generations, if you will. Sometimes when it comes to really challenging tasks, they take more than just, a single career to potentially reduce to practice. As a parable, I think about some of the work that was done to build the great cathedrals of Europe. This is a story that was told to me by a colleague of mine during his 50th birthday over a pint of beer. So maybe that puts it all in context. But he was just talking about the fact that, you think about the mindset we used to have as a people hundreds of years ago. We would undertake tasks that took multiple generations to achieve. And the folks that built in the cathedral scenario, for example, the people that built the basement never lived to see the rest of the building get built. they only could envision the final product in their head. But they knew they had to do their part for the other people to do their part and the other people to do their part, right? And so I think that's an important thing for us to reflect on. And you kind of just, you represented it in a microcosm, if you will, where you've got, young investigators working alongside the more mature investigators. And so I think we need to, just like this beautiful crosstalk of togetherness here, people are already talking about, hey, this made me think of that, or this made me think of that. Doing things together across generations, I think, is a very important thing for us to remember. So anyway, thank you everybody for joining me today. I hope the midterm that we can do this in person. I think that would be much higher quality interaction, and we would certainly enjoy that and have some opportunities for some other things to do. We'll certainly try to stream it all as well. I will do my best to get the YouTube recording uploaded to the website. I think I saw a question asking about the presentations. I'm going to try and find a way to make that, logically post that on the web to our website or something like that to make that available too. So I think with that, any parting comments from anybody before we call this meeting complete?
I just want to thank you, Sonny, for all of you've done. I mean,
yeah,
really, not just for this conference, but the whole program. I've just been so impressed. So thank you.
Yeah, thank you so much.
Thank you.
Thank you, Sonny. Thank you to everybody. Very interesting and also very exciting.
That's very
and
unique.
very strange also.
Okay. All right. Well, thanks everybody.
Okay.
I'm going to go ahead
All
and bring down the systems. Thanks everybody.
All right, take care, everyone. Nice to meet you all
Bye-bye.
virtually.
Take care.
Bye-bye.